remarkable thing that had happened in my lifetime.
Discovery Roger, go for deploy.
Welcome, ladies and gentlemen. It's our great pleasure to welcome you here in the beautiful halls of the Prague Mayor's residence. We are excited to witness how many of you have traveled here to be part of something new. To attend this first of its kind event, we hope that it will be a solid opportunity for sharing your insights and also hopefully gaining some new knowledge about emerging technologies that are blending robotics and some of the most advanced X-ray computed tomography methods. So please welcome to the first RoboCT user forum. Sorry for the waiting in the beginning. We were just waiting to be connected to the live stream. And we can begin. My name is Martin Tiburec, and I'm honored to guide you throughout this conference. Today, 8 esteemed speakers will deliver keynote presentations, followed by a reception networking event right here in the residence. We hope it will offer you valuable networking opportunities. Now, it will be my privilege to invite Dr. Josef Uher, Chief Technology Officer at RadalyX, to deliver the opening speech. Josef, the stage is yours.
Thank you. Thank you very much. Martin is much taller than I, so I have to adjust. So, good morning, everyone. Thank you very much for coming. And when Martin asked me that I should give some, thank you. He's professional. When he asked me to give some like introductory speech or how it should be called, I was thinking what should I say? So I was digging in some archives looking for some pictures, and I found that picture you see there. That's a friend of mine from childhood, and as you can see, the picture is from 2016 when I visited him in the company where he worked at that time, still works there. And we were just chatting what we can do together, and then he said that, look, I'm actually selling these new robots, you know, these universal robots. Maybe you would like to see it. So that picture there is my first contact in my life with like robotic arms. You can see that it's defined very precisely in time. So it's October 24, 10 o'clock in the morning, 15 hours, 48 seconds. So that's really the beginning of the journey. And so back then I asked him if I could borrow 2 robots and just give it a try. You know, what happens if we combine a small X-ray tube that we had with detector and see where it goes. And that's the picture bottom right. So we took 2 robots we could borrow from them and also from Universal Robots, and then we moved everything to Institute of Nuclear Fuels, to the basement there, which was quite scary because the basement wasn't really used too much. So we set up the first experiment, and we thought, wow, this is cool. It's really so nice to combine it with X-ray imaging, and that was the beginning of the story. And to be honest, back then I would not expect that it would lead to an event like this, that we would be here in this place with so many people coming from all around the world. I have to say thank you very much for coming. That we have people from US, we have people from Japan, we have people from all around the world. That's amazing, you know. I really would not expect when I was taking the picture in 2016 that this will that it will go to this place and to this event. Yeah. So thank you very much for coming. Welcome here. Welcome in Prague. For some of you, it's the first time in Prague, so enjoy Prague. Be aware of dangers of Prague as well. There are lots of bars and clubs in the evening. So welcome. Enjoy the meeting. I hope we will have very nice discussions. To me, it is more about discussing and meeting people and creating some sort of community around this technology, because I believe this is an interesting way forward, and it will bring lots of interesting options and possibilities, as you will see during the day. So welcome and enjoy the meeting. Thank you very much.
Dear Joseph, thank you very much for your warm words. And before we begin, let me sincerely thank all of our partners and supporters who made this event possible. This conference is brought to you by Advacam and RadalyX, with the support of Prague Innovation Institute, Czech Aerospace Cluster, Czech Invest, the Association of the Czech Aerospace Industry, and the City of Prague. Thank you very much. And one more note of practical importance. If you have any questions or need any assistance during the day, my colleagues Petra Weinholdová, back at the window, and Tanya Holanová, who are now standing by the side of the hall, will happily help you or assist you. And now we can move and proceed directly to our first keynote presentation. Ladies and gentlemen, the following speech will be delivered by Professor Gabriel Herl of Technische Hochschule Deggendorf. Mr. Herl will deliver a speech titled RoboCT at Deggendorf, Current Advances in Robotic CT, exploring recent advancements, including workflows for easy scan planning and precise calibration techniques. Professor Herl is a renewed researcher who specializes in the robotic CT trajectory optimization and calibration. Professor Herl, if you are here, you are here. The audience is eagerly waiting for your lecture. You can use this mic or this. Okay.
Can I use a mouse too?
Yes.
Yeah, hello. It's very great to be here. Thank you very much. Thank you for the nice introduction. And mostly thank you, Josef, for inviting me and for this great event. It's an honor. Okay, so we're in Deggendorf, Deggendorf Institute of Technology, and this is our system. For the people who don't know where Deggendorf is, it's in the south of Bavaria. We're currently 10 researchers. There's another professor, Simon Zabler. He sadly couldn't be here, but Anton Weiss is here for more technical details, if there are questions. A lot of stuff is happening right now. Currently, we published a review paper. It's about 60 pages long, so there's a lot in there, but it's not peer-reviewed yet. A lot of stuff happening right now. So let's start. Let's start with let's start here. Great. Okay. So let's see our system in action. Here we have two robots. They're both on linear axis, and in between there's a tailgate of BMW, and we're doing a 2D scan of a projection. It's real time. We can see here it's 17.8. On the left side we see, bottom side, the digital twin, and the digital twin we do the planning, and on the right bottom side we see the current projection. So this is live. We do the planning and the digital twins, and it just happens. And now we can see this is a 2D scan. And yeah, this is made by Anton Weiss, one of the PhD students, and he's here. So let's quicken it, let's make it a little bit faster. We can see the system is working, the detector is doing all the work, is moving, and the source is more or less stable. Sometimes some time goes on here, and there was a reorientation, and then after about, we can look at the clock, after about 5 or 6 minutes, the thing is more or less completely finished, and we have a big projection of the complete thing. So if you have a thing here, can place it inside, be a little bit careful that we don't crash, so we have to do the stuff in the digital twin, and then go 5 minutes, and we have a big projection. This projection took about 5 minutes, 350 megabytes, so it's a lot of data. And then, yeah, a lot of pixels. So this is 15K to 11 or 12. Bottom side, again, we see the digital twin. On the right bottom side, we see the current trajectory in real time. And again, it's like 10 minutes before 18 o'clock. And if I speed it up a little bit, let's wait a little bit. If I speed it up a little bit, not that easy. And we can see that it makes something like a sinusoidal curve. To do it smoothly here. Yeah, here it's fine. So it does something like this. And this is planned in advance, just with a Python script mostly. And yeah. And this is finished in about 5 minutes. To be honest, with 5 minutes, the quality wasn't perfect. So hey, we repeated it in 20 minutes, but this is real time. And then the construction result can be seen here. So this is a flyby scan of 20 minutes. It's a 1.5K voxel volume, voxel size of 139 micrometers. Was reconstructed with a standard reconstruction algorithm. And we can see here, we can even see the layers in the 3D printed material. So yeah, even with flyby and very quick, fast scans, we can do 3D reconstruction. So obviously we want to improve here. This is the current work. But RoboCT does not mean that we take long. We can be fast. Okay. Next is usability. We want to do automatic testing, even in complex scenarios. And here we have a cooperation with BMW. It's Jonas Schnitzer is one of my PhD students. And he planned an automatic trajectory, and he has algorithms to do this inside of different regions of car bodies. And we can see here, this is not real time, but this is an automatically planned trajectory. And we can be sure that the robots do not crash with the car body, even in these complicated situations. Yeah, and he uses this for checking defects in car bodies. The main topic here is reachability, don't crash, and finds the projection views that optimize image quality. And this here uses prior knowledge, so I have to know what kind of car body is placed in the system in which place. Okay, results here can, for example, look like this. I hope you can see it. Here on the left side, you can see a rivet, for example. In the middle, we can see a faulty adhesive bond. There's some adhesive lacking. On the bottom side, on the bottom, we see some screws. This is reconstructed with Voxray. One of Voxray people is here too, because sometimes calibration can be a little bit difficult. And in this case, we can use Voxray, and then the reconstruction nevertheless does work pretty well. So, yeah, some real images. Let's go on. Next, like I told you before, the thing with the car body, we needed the prior knowledge. Right now, we want to do it live, without any information about it. We just start scanning at some place, and then want to see, hey, can the RoboCT for itself look good? What's a good path? And we do it with reinforcement learning. And at the start, we have a training phase. That means that we load different kind of objects from a database into the training framework, and then we start with different agents, and they try out different routes, and then we give reinforcement to some of the routes, and after a certain phase, we can say, hey, it finds this thing. So it rewards if we avoid big. Good. Next thing is we want to do mobility, and one of the projects that we get funded right now is that we do 3D CT scans on bridges. So this is a little bit crazy, I have to admit it, but we can use a Betatron of BAM. It has 2.5 MeV, and here we want to try, hey, what can we check in bridges? So we're looking for different defects, and yeah, let's see what happens. And obviously, calibration will be a big part of this project, because we have to bring the stuff there, everything can be shaky. Yeah, A lot of other projects are planned right now. I'm looking very much forward to a project with RadalyX. We are currently planning optimizing RoboCT for aerospace. For example, we have a Eurostar project here. And another project that I'm looking forward is using drones for 3D CT. So if we say, hey, we can do it with extremely shaky manipulators, so why not use drones? And the goal here is to do this to check wind energy plants. And here we have a current project here in hope that we get funded, and other stuff too. Okay. Then I talked a lot about, hey, what are the challenges, what can we do right now? But hey, mostly we can do CT for large objects. We can do it with arbitrary trajectories, we can do laminography, tomosynthesis, we can do helix, we can use circles, limited data, or just arbitrarily placed positions that are optimal for a use case. We can big 2D projections, we can do 3D scans. And if you're interested and if you have objects and you would like to have scans, come to us. Accuracy is about 100 micrometers. Price of is it an easy use case or is it a complex big thing? And yeah, we would like to find more people who want to do scans. And yeah, I think I was relatively quick. Thank you very much again. Contact us if you're interested in scans or just some research. Enjoy your time, and again, thanks a lot for being here. And yeah, thank you.
Thank you very much, Professor Herl, for your insightful presentation. Now there is the floor open for your questions. Please raise your hand correctly and wait for the microphone before you start speaking.
Yeah, thank you for the interesting presentation. You mentioned with one sentence you want to check drones.
Yes.
I'm a little bit wondering, you have to handle heavy weights, maybe, and you have to handle radiation protection.
Radiation protection with wind energy plants is no problem at all because there are no people near this thing. So
where do you plan that? In companies and oil plants? And
yeah, the idea is really to use it on real wind energy systems. And if you're high in the air or maybe over the ocean, then there are no human beings. So if you just do a little circle and say no people are allowed here, that's no problem. I find it a little bit scary, but right now, in this bridge project, we have a guy, Sebastian Schulze from Bauray, and he's allowed to scan on bridges, even if there are cars driving on the bridge, as long as they're driving fast enough.
Passagelos, yeah.
So this radiation project is not a problem at all. Obviously, finding the right drone and finding X-ray equipment that's light enough and still can penetrate enough material is a little bit difficult. But I think that's possible. It will not be possible for every region of the wind energy plant, but in some regions. That's the goal of the project.
Can I ask a second question? If you have to calibrate your robots,
sure.
Many people do optical calibration. Do you also combine that optical and X-ray calibration?
We did test a lot of stuff. We did compare a lot of stuff. Here, Anton is a guy that did this. The best result were when we did a second calibration scan. We did scans with laser trackers, for example. Can be done. It was the most easy and cheap way. I don't know. Do you want to add something? Sure.
So you can actually calibrate the whole system as a unit for both of the robots. Classical robotic calibration using also X-ray data from a calibration object and afterwards applied to the scans. You lose spatial resolution, but you still can do about 150 to 180 microns without a secondary calibration scan afterwards for several weeks until you have to do it again.
Are there any more questions? I see a hand raised.
Thank you, Gabriel, for the nice overview on your assets. I just wondered about the calibration of that helmet. Is that relying on the accuracy of an external optical metrology system to pin the markers, or is it intrinsic?
It's an iterative process. So it first finds the blobs inside the projections, and then that it tries to find which blob in which projection corresponds to which other blobs in other projections, and then it tries to find which position is it probably in 3D space. And then it does an iterative optimization. And yeah, it works really well. Paper will be there soon. And then we have to obviously test how much markers do we need, how much do they need to be in different regions, for example. Obviously, if there's a massive object, we can't place markers inside the object, so there's still problems. But if we have the possibility to put enough markers on it, and we can see the markers, and we can do the calibration. For example, for a bridge, that will be difficult, because, hey, the question is, can we read the markers good enough, and can we place the markers on the right spaces, the right spots? So, yeah. But in theory, we can do, for example, 2D, if there's just a system that normally only can do 2D projections, then we can do 3D reconstruction using this technique.
Okay, cool, thank you.
Thanks.
Thank you for the wonderful talk.
I was really surprised that it's like it could be moved to the object, it could be bring to the object, and you can do whatever.
I mean, obviously the people of RadalyX have done this. We haven't. But this mostly due to time reasons. We look at different use cases, and yeah, I would love to scan cool, beautiful artworks, and we should do this in the future, but right now, due to time reasons, we tested it on more or less boring objects, that we have here like a bike or something from a car. Obviously, could be cooler stuff, and it will be. So if you are interested, for example, sure.
All right, yeah, I see another hand.
Actually, just a suggestion in mind, but I was at a conference 2 weeks ago where somebody was presenting scans of mummies and bog bodies around the world. Actually, very cool presentation. I liked it very much. And they had a serious problem to actually put Ötzi in a standard CT gantry scanner, because this guy actually is twisting his arms like a Nazi style. So the thing is, actually, they were wondering how to get like a good scan of this thing. Maybe you want to.
If you have context of the people who have Ötzi and you can scan Ötzi, obviously, I would love to.
Might be a nice paper.
Sure.
Again, thank you very much for your questions. Don't hesitate, please. We are on time, so you can ask your questions more next 10 minutes.
Way too fast, I'm sorry.
Hi, thank you for the presentation. About the robot, is there any possibility of electronic damage on the robot? Because you're moving them while scanning, so they're under radiation. Is there any possibility of electronic damage?
In theory, there can be damages on the electronics, on certain sensors, for example, or that's why sometimes you have to be a little bit clever. Don't always have the rays on the same, or don't put certain sensors inside of the main beam, but we haven't heard about any problems with the robots. More like if there are extra sensors or anything, then there can be damages, but it's not a big problem.
Yeah, so you do not have any shielding on the robot,
as far as I know, there's no extra shielding for the robots, no.
Okay, thank you.
Well, if there are no more questions, I have to thank you, Professor, for your nice and interesting talk. And we will be looking forward to speaking with you and talking with you in the discussion later. Thank you very much, Professor Herl.
Thank you.
And we now invite...
That's a kind of spin-off which is focusing on inspection of art. So there was a question about inspecting sculptures and art pieces. So that's what we do in Inside Art, and there will be one more talk in the afternoon focusing on that. Nevertheless, so we started 2016, and as I said before, we were developing the idea further and further up to a point where I would say we have now like a mature enough system that we can deliver to our customers, and we have already machines installed at our customers in variety of industries. Very surprisingly, the very first customer wasn't aerospace, wasn't automotive, nothing like that. It's a company here in Czech Republic, PSI, which builds like automatized greenhouses for phenotyping. So they study growth of, they build greenhouses to study growth of plants, and they measure all sorts of parameters of these plants, and they wanted to have X-ray imaging stations, so that was our first customer. But now the focus is mostly on space, aerospace industries. So the basic principle, I can probably go very, very, very quickly through. Everybody in this room knows. So X-rays is a game of shadows, so we are also measuring shadows. The difference is that we have the photon counting detector on one of those robots, and photon counting detectors bring lots of advantages for X-ray imaging, better image quality. They are opening new applications which were not possible with older types of X-ray imaging detectors. Jan elaborated the mutual position of these robots because that's important for the computed tomography, and we were able to scan the attachment landing gear to fuselage. This is a newer exercise that we did last year. This poor aircraft had an accident on the final, during the final, let's say, phase of the landing. The engine cut out because there was a problem with fuel delivery, and the pilot had to land, crash land about 200 meters short of the runway. And during that landing, the landing gear, which was already out, ripped off, broke, and hit the skin from beneath of the wing. The skin detached, and the right wing hit the ground. And so we knew that there is like a detachment, you know, that the skin is detached from the main spar, so that's the support that is running through the aircraft. So we knew that it is detached, but the question was, is there any defect inside the main spar? Because that would mean that's the end of the fuselage, it would have to be thrown away. And so we packed the system and took it to the middle of nowhere. It's like a garage somewhere in mountains, you know, in Czech Republic, where they are going to fix the aircraft. And we had to improvise quite a bit because this was really not a spot for like X-ray imaging. However, you can see the flexibility of the system. So we are setting up the machine, we are calibrating the position of robots mechanically in this case, but we can do it with X-rays, attaching source and detector and placing both near the location where we need to or we would like to measure, then doing some more calibrations and setup in the software and then running the measurements. So you see now the robots are measuring the main spar, so that's where, do we have a laser pointer here? Yeah, which one is it? Yeah, okay. So the main spar is actually here, yeah. So that's a support that runs through the aircraft. And there was a question about radiation protection. So in this case, it was combination of shielding and distance. You know, in circumstances like here, it's relatively straightforward. We helped ourselves with some like LED screens. You can see them here. But in reality, about 15 meters away from the place where we were measuring, there was background. There was no radiation present. That's one thing. Second thing is that because we have the photon counting detectors, they are sensitive. They are more sensitive, so that means we can use weaker sources, and again, the radiation protection is easier. So here is one of many scans that we did on this aircraft. So that's the main spar. The good news for the owner was that we did not discover really any damage that would be correlated to the accident. However, there were lots of strange things happening in the layering of the carbon fiber in the material. This is yet another similar accident. Here, the landing gear closed by incorrect setup of the aircraft. The pilot didn't go through the checklist at the beginning. That's why it's so important to go through the checklist. So he didn't do it correctly, and when the aircraft was just lifting off, the landing gear, because it was set to close, started to closing. It has automatic closing, but because the aircraft wasn't yet flying properly or enough, it landed up on the belly, and it was sliding on the grass, and it got some damage. So again, the same story, we took the system and we brought it to the hangar where the aircraft is placed, and we did our exercise of calibrating things, and we measured. So there were some cracks that were visible on the surface, but unfortunately we discovered also many others that were hidden in the structures, and because it's quite important part of the fuselage, it seems that this aircraft has a bad luck. You know, they may have to throw it away. It will be difficult to fix it. Now, okay, so back to robots themselves and the properties of imaging. So one big plus of photon counting detectors for non-destructive testing, especially in aerospace, is that the photon counting detectors deliver broad dynamic range. So what does it mean? Is that in a case like this, it's our test object, a dry rose, where we have glass vase and a dry flower. That's something very difficult for X-rays, because you have very low attenuating structure here, but you have relatively highly attenuating structure there. So standard X-ray imaging devices would have a trouble to show everything in one shot. You would have to take multiple shots very often, and it's not that easy. But with photon counting detector, we can do it, which means in combination with robots, we can really scan difficult objects, in difficult situations. This is an example from art. I like it a lot because if we look here, so this is a silk on the puppet, and this is the structure of the nail. So you can see it's a massive difference in material properties from silk to steel in one picture. In terms of the resolution, detectors themselves can resolve 50 microns. I think Jan will be talking about it. However, when the inaccuracy of the robots kick in, the resolution goes a little bit down. So we have around 60 micron resolution when scanning with the robotic system. And here are some examples of scans. So lots of it is carbon fiber, honeycomb structures, propeller. This is the wing from Orly-chan. Foreign objects, some piece of cloth inside, that's also quite, inside the wing, that's quite well visible. And many others. So ceramic heaters, that worked also quite well. Batteries, everything is around batteries. Everybody's scanning batteries, including us. So you can see that here we use 100 kilovolts. Composites were measured with 50 kilovolts, typically the same detector. We don't have to change anything. Welding on aluminum structures, also quite important in many applications. This is a porosity in aluminum, so that's for casting. And high resolution image of a weld. So we newly integrated X-ray tube that has a tiny spot, 5 micron spot, which means we can use magnification and we can magnify the images geometrically, and we can go down to 5 micron resolution in X-ray, 2D X-ray images. It's a bit difficult to do it in CT because the inaccuracy of the robot would spoil it, but in 2D images we can definitely take 5 micron resolution. And this is yet another example. It's a strut of a landing gear of an aircraft. This aircraft is particularly important for me because I sat in it several times. It's from our air club, and guys ask me if I can check if the landing gear is okay. So we took X-ray scan with our system, and for comparison we took also an image on film. So you can see that the difference is clearly visible. So the film, which is very commonly used still for non-destructive testing, including aerospace, has quite some limits compared to our technology. And this is yet another example. So that's a stainless steel part, which is about, let's say, 3 centimeters in diameter. And top image is taken with standard setting of the detector. Bottom image is just increasing energy discrimination threshold. So we can cut a certain part of X-ray wavelengths and use only the higher energies. And that improves the contrast in images, which is again quite important for like computed tomography and many other applications, because you need to have very good input images. That's always important. This is a scan of a painting. I will be talking about it in the afternoon. That's something we measured in Inside Art. The challenge here wasn't so much the physics or the imaging itself. The challenge was that this thing was bloody expensive. It was 400 million estimated price in euros of the painting. So you can imagine that everything had to work 100%, not to touch it, not to scratch it. And you can see that even robots can be made safe enough so that we could dare to scan such a valuable piece. Obviously, we had some extra safety measures like these laser gates, which were connected to the controller of the robot. So, images with focus. So, tomosynthesis explained on this object here. So, if you have a structure like that and you take X-ray image, you get this mess. So, all these structures are on top of each other. Moreover, depending how far they are from the X-ray source, they have different magnification. So if you are X-ray imaging something complicated, it might be rather hard to understand what you are looking at, and it might be rather difficult to identify that there are any defects. However, with robots, we can just change the trajectory of the scanning. We already saw it in the previous talk. So we can change the trajectory, how we are moving around the object, and we can, in a way, focus the X-rays to a certain depth. It's not a full computed tomography. It doesn't give you such a good depth resolution as a full computed tomography, but it gives you good enough depth resolution to separate structures from each other. And that turns out to be quite important because A, it's much easier to understand the image. B, the kind of defect detectability goes up because you can separate these structures from each other. And there is another benefit. There was also a question about measuring these dimensions. So in this image, it's rather difficult to measure anything because you don't know the magnification. But after the processing in the computer, we have everything on scale, so you can do basic metrology here as well. So this method applied on a honeycomb, which is commonly used in aerospace. You have focus on one side, you have focus on the potting around the insert, and you have a focus on the other skin of the structure. Here, another honeycomb just with water in those cells. That's a big problem in aerospace. You have to avoid it because if there is water in the honeycomb and the aircraft goes up to high altitude, it may freeze and it may cause a damage of the honeycomb. So water detection is quite important. And in this scan, we saw this kind of weird pattern. We didn't know what that is, and we were wondering if we have some problem with the detector, and it turns out to be a description of the sample. So it just can give you an idea how good image the camera can measure. This is yet another example of the tomosynthesis. It's a carbon fiber propeller for eVTOL aircrafts, so for these aerotaxis. And left is 2D image. So the propeller has a like laminated piece of wood inside in the center. Don't ask me why wood, but that's how they do it. And here we can see quite easily these big cracks between these segments, but not really anything else. But in the tomosynthesis, we start to see also these hair cracks around the insert. It's the same scan. This picture is the same scan. Just the gray scale is changed to see the layering of the composite. So here are the layers of the carbon fiber in the same image. Yeah. And back to our aircraft. Here, because we applied the tomosynthesis, we can see how deep the crack is. So not only that there is a crack, but we can also estimate how deep the crack is, and also what is the shape of the crack and the different depth. Now there are some limitations. As I said, you don't have such a good depth resolution as in case of computed tomography, so that can be sometimes handicap. On the other hand, the tomosynthesis is good to measure region of interest, something really large. You know, if you have a link, then this is a very good method to use it. Yet still, if you would try to visualize the data that you have measured in 3D, you get something like this. It's a cube of mass. You cannot really visualize it in 3D. And that's why we combine the tomosynthesis scan with like laser profiling. So we measure the outer shape of the object, and we sort of carve out the real structure from the tomosynthesis. And then the result is something which is very much close to computed tomography. Okay? That very much increase, again, the readability of the structure. And for that purpose, in order to measure the shape, we have integrated this little laser tool here, which measures the distances. So the robot first scans the shape, and then we use that within the reconstruction. Now, if the structure allows, if we can rotate around, we can go to full 3D. So you can see guys are moving again the system to the aircraft, positioning it freely. This is a big advantage of the collaborative robots. I forgot to say that. We are using universal robots, so those are meant to work with people on production lines. When they feel a collision, they stop. For us, it's not really an advantage for like preventing collisions with humans, because anyone can be around when the X-rays are on anyway, but it is very useful to prevent collisions with the sample. And also it gives us an option. Can I go back? Yeah. We can also manually position the robots in the location. That's quite a big benefit. Nevertheless, so the system, the source detector rotate around the object, and we measure full CT as we saw in the previous talk. And here are the results of such scans, all sorts of things. Again, honeycomb. In this case, we have stainless steel pipe inside the honeycomb, so we were able to suppress all kinds of artifacts that are normally present, automotive parts, even some preclinical research. You know, the application range is very, very wide. Some first results for medical applications, so it's vertebra. It's a 3D printed piece, and we were testing on how far we can go with the resolution. And the automotive bits and pieces, Czech Republic is of course big on automotive, so detecting some porosities in here. This is a nice stuff. The real thing we cannot show, so it's just a surrogate object. Let's say that you have a structure of light materials, and then you have a fastener which is of titanium or steel, basically something heavy, and you have a defect underneath that. So if you take a standard X-ray image, any defect is kind of shadowed by the high attenuating piece of the material which is there. You can see stuff only if it's protruding from beneath the head. But because of the flexibility of robots, we can sort of peek underneath the fastener head, and we can look around the fastener, and we can see any kinds of defects or foreign objects all the way to the screw or the fastener itself. So that's really beauty of robots and flexibility it gives you. This is yet another example of glider wing, and in this case we measured only 105-degree range, so we couldn't measure full computed tomography. Yet still we are able to see all sorts of defects and porosities in the leading edge, even some sort of dent in the layering. And if we do 3D visualization, we see it looks like somebody pressed a finger against the layers when they were putting it into the mold. Now, I mentioned the robot-to-robot calibration. So one way is to connect them mechanically and calibrate the mutual position of robots, but that's not very practical if you have really large aircraft and you would like to have one robot inside, the other one outside. So for that purpose, we have developed a method to calibrate using X-ray beam. The beauty of that method is that it's independent of the structure. So even if you are shooting through something complex, still we can calibrate the mutual position of robots, and then we can use them for the computed tomography. And then there are lots of other methods like X-ray backscattering. Again, you will hear in other talks about these methods. The point is, for example, in this case, that we can have both X-ray source and detector on the same side of the object, and we can scan from one side with X-rays. That's one benefit. Second benefit is that we can measure, for instance, gaps between large panels, something which otherwise would not be visible in X-ray transmission mode. Ultrasound would tell you that there is a gap, but it wouldn't tell you how large the gap is. But this method can tell you some estimate how large the gap is between these panels. And because we have robots, we can scan and we can do some clever approaches, and we can measure single-sided computed tomography if you want, with the backscattering. Ultrasound, that's another one. Even though we are very X-ray centric, we have to admit that there are situations where the X-rays are not the good answer, even the backscattering, such as here. So if you have impact damage in carbon fiber, then X-rays will not really tell you anything. But ultrasound will tell you that these layers are detached from each other, so there is a delamination. So it really makes sense to combine these methods together, because each is showing you something else. And for that purpose, we have integrated so-called laser-excited acoustics. So that's a method where you have excitation laser which hits the surface, generates a shock wave that propagates through the object, and then we are listening with microphone from the other side. Robots are important in this case because, especially in aerospace, nothing is flat. Very few parts are really flat. So robots are good to navigate along the curved objects. And more modalities. X-ray diffraction. This is something we believe has a massive potential. Again, Jakůbek will be talking about it later today. In this case, you can see X-ray diffraction pattern measured in and outside of the heat-affected zone of a valve. You know, that's something which is really has a massive potential for all kinds of applications in production. And then Dr. Kotterli will speak about application in forensic analysis. So for that purpose, we are adding more modalities, such as all kinds of hyperspectral cameras, X-ray diffraction, as I said before, and X-ray fluorescences, and more hopefully will come later on. So again, you will hear about it in other talk. And software. Everything is revolving around software, so I think we did already quite a good job in developing user-friendly software that shields you from the complexity of robots and still gives you a good option to, or good flexibility in measurements and data reconstruction and calibration. All that is quite important. And so to wrap it up, sometimes we are joking that we are building like a Swiss knife for non-destructive evaluation. So you attach to the robotic platform the modules that are suitable for your job, and then you do your measurement and you choose whatever is suitable for your case. So thank you very much.
Thank you very much, Dr. Uher, for your provoking speech. And now it's time for another discussion. Please, again, wait for the microphone, raise your hands. I see Sascha Senck asking.
Thanks, Josef. Very nice talk. One question concerning the mobility of your system, and it's also a bit of a question to Gabriel concerning the drones. How mobile is it when you have to attach like a tether or a tethered system, because you have to have a power plug at some point? Probably it's not, maybe it is working with a very mobile battery solution also?
Well,
for some minutes at least?
Well, in principle, yeah, you can power it. The theoretical maximum consumption of the system is about 2 kilowatts, but that's theoretical. You know, in reality, the consumption is much lower. So you can have some sort of batteries or some petrol generator, electricity generator. You know, so I don't think that the power is an issue. Truth is that the system as is now has some limitation in the portability because the pedestals, for example, that we have under these robots are quite heavy. So we are now working on ways how to make it even more portable, have some sort of tripod like we have here. You know, it has to be more robust, of course, but something that would let us to set up the system within 15, 20 minutes, you know, to get it ready for the measurement.
I see many hands. Okay, thank you.
Hi, Josef. Yeah, nice talk. I think it's really interesting how you're able to do the material differentiation. And I was just curious on, you know, how's that performed, and do you have to do any kind of calibration?
Well, you know, there will be more about the material differentiation in the afternoon, because we use that quite a lot for art inspection, because there, you know, pigments are of all kinds of types. And so we are using changes in X-ray spectrum. That's the beauty of these detectors, that we can measure X-ray wavelength or energy, and we can use that to recognize sort of like the trace of the material. Yeah. So that can be used. There are, of course, some limitations. You know, if you are talking about plastics, it's much harder because it's always carbon, oxygen, hydrogen in different combinations. You know, so that's more difficult to recognize. Once you have some heavier elements, then it's easier. So that's a really broad topic. Again, Jan, I think you will be talking about it. Yeah, he's nodding, so he will speak more about how to use these detectors and what kind of detectors are there. You know, because different jobs may require different detectors to discriminate materials.
Okay, thank you. And a second question was, so you on your tomosynthesis work, you were basically taking, you know, Z depths, and you said the resolution isn't good, but what is that resolution like roughly in terms of Z resolution?
Well, that's a little bit difficult question, because the depth resolution also depends on the size of the feature you are looking at. Yeah, because try to imagine. So you have this object, and you would like to see what's behind it. So, and if you have only a limited range of angles, then you don't really, if it's too close, you will not see it. Yeah? You have to increase the angle to start seeing it. If you have it the other way around, then it's much easier. The pen you will see even from small angles, you will get the depth resolution. You know, so that's one of the limitations of the tomosynthesis, that you have that sort of like dependency. Having said that, there are groups. There is actually a group in Texas and University of Arlington, and they seem to have a nice tool how to improve the reconstruction. So that's something we can talk about. And also there are other options for the future as well.
Okay, thank you.
Thank you very much for your questions. First hand was raised over there. You have the speech.
Thanks. Brilliant talk, as always. No, but two questions. First of all, you were talking about laminography, but of course you're not limited to linear laminography with the robots, right? So you basically can do like some sinusoidal additional data acquisition. How much do you estimate the gain by having this additional freedom in laminography to?
Well, first of all, it's a very good question. First of all, one issue I see around the robotic systems is the terminology. Because, you know, with the flexibility of robots, you can combine all sorts of approaches together. You can have 2D imaging combined with just parallel movement of detectors. You can add some angles. You can have a helical scan, cone beam scan. Everything can be on one pile. You know, so first issue is how we speak about it. You know, and that's number one. Number two is, obviously, again, as I was here explaining the tomosynthesis, it's all about like what you are looking for and how many angles, how many points of view you add. You know, in my opinion, the robots or the robotic approach has the benefit to sort of mimic how humans are looking on things. You know, if you have a glass with water and you would like to see bubbles inside, that's an example I always use. We also don't rotate like 300 degrees, 360 degrees and do some CT reconstruction in our mind. We look from several angles and we get the idea what is where. Yeah? And we keep adding the angles until we think we have a good idea about the 3D structure. So with this technology, it's exactly the same.
So it could be real-time adaptive scanning at some point, basically, where you say, okay,
yeah,
I want to look at this feature, I basically
that
refine this trajectory in real time, basically saying, okay, this is, and this would be a very strong interactive system, right? Because
absolutely,
it would be very natural to operate.
Absolutely, absolutely. Actually, at some point, we had also like an option to control the robots with a 3D joystick. So, and there were many situations where just live image was enough. You know, we had a guy who brought a bike frame, and he knew what he's looking for, and he just took the joystick, and he was like, computed tomography, we find a step. Yeah.
Okay, and regarding the strategic point of view, regarding the size of the sensor to how quickly you can scan, is it also, so we also use Medipix 3 in a Fear 1 configuration from Advanced. Does it make sense to go to bigger formats, or is the data or the cost really a killing factor?
Actually, also a very good question, and we get it quite often. Yes and no. If you have a larger detector, and let's say you are measuring the tomosynthesis, so source and detector are moving together, that's the easiest approach to the tomosynthesis. Then having a bigger detector means you have kind of wider range of angles, yeah, from the larger detector. But still the stepping you should keep small because that gives you kind of the fine step in the angles. Yeah. So bigger detector doesn't really speed up the measurement, but gives you better data in this case. Yeah. And it very much, however, if you have 2D image, of course, then the source is stationary, and then you can measure with larger step of these tiles, so there it speeds up, you know. So it's kind of like yes, no, depending on the situation. And truth is that the speed of the measurement is definitely a topic. That's why guys in Deggendorf are also working on that continuous move and all that. Absolutely, you know, speeding up the measurement is a big topic.
And one last question regarding the scintillator from cadmium telluride. What do you think are the challenges for the high power applications? Or in case we move to higher energies, where do you see the limitation and where is the sweet spot for resolution to the scintillator?
Well, because it's a direct conversion, so the radiation is changed directly to a charge, which is processed in the pixel, and the charge is attracted by the electric field applied. You know, there are much less pronounced effects like the light. There is no light spread. You know, this charging and so on. So, what that means is the detector can go to much higher energies compared to just charge integrating devices without any trouble. So you can really use the same detector for composites with tube set at 50 kilovolts, 40 kilovolts, but you can take the same detector and use it on accelerator with 3 MeV, no problem. Yeah. So from that perspective, there's not really a limit.
All right, we have maybe time for one last question, if there is any. If not, I would thank you, Dr. Uher, for your speech. Ladies and gentlemen, and we will now take a short coffee break. I hope you will appreciate it. You are invited to enjoy refreshments, snacks and drinks in the side hall, e.g. the coffee break arena, where the route is prepared for you. And just one notice, in your conference kit, you can also find a questionnaire. If you can fill your ideas for tomorrow, roundtables in it, we would appreciate it. And that's all. Let's return back here at 11:40 sharp to continue with a keynote by Dr. Marek Kotyly. Thank you very much. I would now like to introduce Dr. Ewert. Dr. Ewert will address
terminology, for instance, runs out of order. People publish, make own definitions, and you do not talk on the same thing if you talk on something. So we have in Germany 2 companies. This picture is from VisiConsult. They have a very nice tool to automatically detect irregularities in casting and welding and other materials. We have another company, Sentin, and they are also supporting the standardization. Then we had, beginning of last year, a first workshop, and already later we had a series of workshops, and then everything got disturbed by the Artificial Intelligence Act of the European Union. And so things have to discuss from a different viewpoint anyway. But at the end of last year, we have established a new working committee for artificial intelligence. And then I was thinking, well, that is somehow parallel to that what we are doing on Robotic CT. It's also quite early, but the same thing happens. People talk with different terminology, with different ideas how to work, and it would make sense to make a standard, even if we know that after some time we need an urgent revision. Yeah, let me come first to the standards, because we have heard from Mr. Herl the presentation on Robotic CT. So I want to inform you that we in Germany started to make a new standard on non-destructive testing for construction, for civil constructions. Size degenerates. It needs some measurement procedures to surveil it. So we had 5 standards at the European Standardization Organization, CEN. We have deleted an old one, which was too expensive, too slow. We have increased the radiographic pinhole camera method by digital detectors. You see some pictures. I just choose one from Covotest to show that you can do that with a digital detector instead of a film now. It runs much faster. We have discussed that with the ISO committee. These standards will go to ISO now. The part 1 is already an ISO standard. Then we have an edge method that was already was originally introduced as a method to measure from a hole, not a pinhole, just a big hole, from the edge unsharpness. This is already in the ASTM standard published, and we want to bring that also as an ISO standard. And last but not least, of course, you need to do something with microfocus tubes. We have updated the standard for digital, but the point is this standard does not work below 5 micrometers. When the standard was published the first time, 5 micrometer was the top of X-ray tube design. Nowadays we talk on nanofocus tubes. Yeah, so in the yellow box you find 2 new methods. Many people use already on the yellow box on the right side. They use already the GMA target, that is a line group gauge. We had a big discussion with the companies who produce X-ray tubes. This gauge is calibrated or in line width, and you have to use a factor of 2 to determine the focal spot size, which was a, say, a controversial discussion with neutral words. And then you have on the other side a hole. You see the picture of a hole here. This is the hole, and there's an edge unsharpness. Now you take profiles around the hole, and you use a CT algorithm, modified CT algorithm, and you can reconstruct the focal spot shape, which is comparable with a pinhole maybe of 1 micrometer thickness. You see, you can generate pinholes with 1 micrometer thickness, but then you can welcome each photon with a handshake. So this is a compromise which was developed in a European project, NanoXpot, and target is also available in the meantime. So this is a target what the project was has designed. And you see here an example, the line with the straight lines, also not the dotted line, not the dashed lines, the straight lines are showing what you would expect. And due to the unsharpness, you get a lower modulation here, and you can make a numeric fit, and you can determine the focal spot. This is the part for the line group patterns. And so you see here from 4 micrometers to 63 micrometers line groups. The European Union requires in the meantime that if you get some funding, you also have to produce a product. So this product is available. If somebody is interested, I can tell you where you get it. Okay, you may see something here, but anyway. So then why do we have here the disk structures? These disk structures have been introduced to make exposures like this one, and now you evaluate the unsharpness of the edge. And then suddenly you can find a case where you have a central spot and a small side spot. This was really measured from a microfocus tube. What happens? The microfocus tube burns a hole. That changes a little bit the electronic focusing, and then the focus shifts over the burn-in a little bit. And then it adds a very small spot, and many manufacturers have provided targets you can turn so that you get a fresh surface as soon as you observe that. The only problem is you need to observe it because you don't see immediately the unsharpness. This is the effect. So the software is freely available, and information can be requested to me. Yeah, and then we have seen already a picture of the duplex wire. The duplex wire is a gauge which is known over probably more than 50 years. It was invented not in Germany, it was invented in British Institute for NDT. We have now gotten the request from aerospace industry to add fine wire pairs. We can in the meantime buy duplex wires with finer wire pairs. We have seen already one in the presentation. Then we get new detectors. You see here round detector. Many companies come up with round detectors now, also digital detectory which you can bend to fix it for inspection of pipelines, for instance. And we have now developed a flexible duplex wire for the case that you can make a quality assurance of the detector, because bending may generate larger distances between pixels over the time. So you need always the quality assurance for the detector, for the tube, and for your robots. That is the next step then. So we have another duplex wire, which is made from small pairs. This is for high energy. You see at Fraunhofer here a test with a linear accelerator, 9 mega electron volt, and 100 millimeter of steel, and a high energy detector. And you see this new gauge has much better, less noise than the old one with the wires. So these are the parts to test things. Then, of course, we have made 20 years ago a standard on film digitization. The typical scanner that people are using for NDT is a ray scanner from Japan. But nowadays, you get very nice cameras, astronomic cameras, which allow a long integration. And you can make a scanner which is probably 10 times faster to get high-resolution pictures from this Welt, for instance. It's a high-pass filtered Welt for better presentation. So, then of course the welding standard we have just revised in 2022. The German version came 2023. The weld inspection with digital detectors, and unfortunately there is a mistake in that standard, so that will be solved by a corrigendum, only for people who are doing weld inspection, that you may know that. And then let me come to the standard practice for radiography from our friends from United States, ASTM. And they do not really use radiography with a very high resolution. Typically what they do is what we call class A testing. And you have here some numbers for the spatial resolution, which are relatively low, also unsharpness or spatial resolution, whatever. And they have added the measurement of contrast to noise ratio in a hole. So the mistake in the standard is that it basically does not describe what hole you shall do, because all holes have the same contrast noise ratio typically, but some of the holes are not visible because the human eye integrates over the hole diameter. Anyway, to get rid of the shading, you see that is black, that is white here, and here is that's the white side, that's the black side. You have to use a 2 or 3 hole measurement tool. The only tool for that I have seen in the VisiConsult viewer. I'm not sure if some other have also done that yet, but I just have tried it, and you rotate until you see the maximum, and then you can find the value. So, if you have a detector, I'm wondering if Advacam has it. The standard says you need to have a spider net-like graph with some measurement data for commercial issues. The one is basic spatial resolution, contrast sensitivity, efficiency, image lag for CT, very important, normalized signal to noise ratio, that is the efficiency part, and the material thickness and an isomaterial thickness. So most people did not realize that nowadays you have to have 8 corners instead of 5. No, 6 corners instead of 5. And this is what we expect from each manufacturer of digital detectors, that you provide a graph like this one for the American standards. Yeah, and now let me come to computed tomography. Computed tomography without robots at the moment. We have ISO standards, part 1 to 4. They are very old. It was originally the EN 16016 from 2018, and we decided to make a minor revision. That means we had some mistakes in translations, some unclear wordings. That was corrected, and it will be published 2025. Also, some are already published, some are just in the pipeline. So then, what we have is a new ASTM standard. This is, the most people don't know that. That was published last year, the standard 2 years ago. That was published as cone beam computed tomography examination. We have some requirements for quality assurance and system qualification on the regular base, because we had many people from aerospace industry inside, and they say you have to have your your quality assurance of the detector, otherwise we cannot accept that for our inspections. NetCap already uses the standard. So you have to do quality assurance, you have to measure contrast to noise ratio, contrast discrimination function, MTF according to the standards given here, and you have to measure the monitor on a daily basis, double wire IQI for detector inspection, and you can use, and it's described for how you use it, reference quality indicators that are parts which are close to your object to investigate. So, and it requires a measurement of a pore for 2.5 if you have at minimum 3 by 3 times basic spatial resolution in the pore. Basic spatial resolution was defined as MTF 10% for computed tomography. So then we have a revision ahead from the ASTM 1441. We will implement that detailed detection sensitivity, and then we have the revision of the standard practice 1695 ahead. Also the detailed detection sensitivity has to be included. And we have a new project, a new European project together with ASTM, the direct determination of computed tomography detailed detection sensitivity. That means we want to generate a universal test object to test the quality of a CT machine just with an easy way. Already, if you use volume graphics, for instance, you can measure the CDD, contrast detail detection. It says if the diameter increases, the contrast sensitivity you need to detection goes down, and you see the difference between a theoretical line and a measured line. Then you correct by the MTF, and you get here the range of visibility. Visibility means you look to a cross-sectional image, and that is the smallest porosity you can detect. This already is required in the standard to measure CDD and MTF, but the new point will be to measure that detail detection sensitivity. What happened now? I pressed something wrong. So how does it work? Imagine you have here two different disks, 2 and 3, and that disks have holes at the intersection of that spikes or spokes and the rings. There's a drilled hole, and you have drilled hole of different diameter. So what happens if you make a CT slice? In the small disk, you see here 1, 2, 3, 4, 5, good willing 6 spokes with holes. Holes are already different diameters. But if you have a larger object, the detail detection sensitivity goes down. You see 3 about. So this is a test object. You can in the morning and in the evening, you can put it on your machine, and you see if something changes. You would nicely see change of unsharpness by robots, for instance. And the idea behind is relatively easy, but making a standard which gets accepted is a little bit more complicated anyway. So then, at the end of my presentation, I'm wondering, what can we do for RoboCT and standardization? The good news is we have already one reference standard from our colleagues from ultrasound. So they have already started. So what do we need? We need a guide and a terminology. That's what is typically the first what you do. Then we need a qualification of the complete unit for manufacturers. If you want to sell a system, you have to make some test to say that is my accuracy, that is, okay. Is it on? Sorry. Okay, I'll go away from that. So you see here then the qualification for manufacturers. You also need a user qualification, a test object, what the user can do, the morning and the evening, whatever, and see something that change calibration of X-ray tube, calibration of robots, whatever. Then we have the practice for the different usage. 2D radiography, practice of CT laminography, we already have seen here, that's from a video of BMW. We have already seen examples of that. Then practice for industrial sectors, backscatter, was also mentioned in this meeting here. So then, of course, we could think on welding, piping, casting, corrosion, aluminum, rockets, ammunition, rockets. With the Ukraine war, that comes more and more to the interest. If you have a gap in ammunition, then it will explode instead of go to the enemy. Corrosion, buildings, bridges, already mentioned, cars, windmills, ... So that should be discussed tomorrow. As a summary, I can say de-energified artificial intelligence was for me an example to get a new element in our scientific community for standardization. We should follow a similar procedure like them. Then we have the revision of the casting standard, a revision of new standards for the measuring of focal spots, including spots smaller than 5 micron. We have even a first gauge available. We have the revision of standards for film digitization, which is not that important for the community here, I guess, but anyway, that's a bridge from film to digital. We have new wire double plate IQIs, flexible IQI. We have for the weight inspection some corrigendum, one for integration. My fault because I missed it in the correction. ASTM 2698, standard practice for RT using DDAs with unsharpness determination, geometric and detector unsharpness, compensation principle, and new CNR measurement under revision. Then we have the revision of the manufacturer characterization of DDAs. New CT standard practice 3375, which most people don't know yet, but aerospace industry will put that to the NetCap requirements. And standard draft on DDS, which is not yet finalized, but is under work with support of a European project. Yeah, and tomorrow we will have the discussion for the standards for RoboCT, and I only made some points which we want to discuss tomorrow, not today, to see how far we can come and who may be interested in this one. Yeah, that's all what I have to say. I have no idea if the time was too short or too long. Thank you very much.
Thank you very much. You were on spot. It was just accurate. Thank you very much. And now we have about 10 minutes for a short discussion with Dr. Ewert. Are there any questions?
Which is always difficult for standardization.
Yeah. Then I guess we will have more 10 minutes for the lunch.
Okay.
Okay, that's all right.
Thank you.
Thank you very much, Dr. Ewert. Yes, now is the time for break for lunch. Lunch will be served in the banquet hall, which is a room this direction. After lunch, we also invite you to experience the virtual reality if you don't have already. It's in the room on the other side of the complex. And please also, you are welcomed to hold private meetings because we have also here two B2B meeting rooms behind me where you can do your discussion in privacy. And please don't forget, if you don't yet, please fill in the questionnaires in your kit for tomorrow's discussions about the standardization, for example. So now the break will be until 13:30, and then we will resume with a short speech by Prague Innovation Councilor, Dr. Daniel Mazur, who will come to make a short greeting. It's not in your schedule, it's a little change in the harmonogram. So then we will continue with Dr. Sascha Senck. So bon appetit and thank you. Ladies and gentlemen, I hope you enjoyed your break and had a moment to recharge. You are back. I'm happy you are sitting. I hope you are convenient. Now please welcome Mr. Daniel Mazur, Councilor for Innovation of the City of Prague. Mr. Mazur, thank you very much for your support and for making this venue, the residence of the Mayor of Prague, available for our gathering.
Good afternoon, ladies and gentlemen. I'm very pleased that I was able, with the Mayor of Prague, to procure you or arrange for you these halls in the official residence of the mayors. So the city of Prague is one of the more developed regions in the Czech Republic, and as such, a lot of its productivity and innovation happens without any encouragement or hand-in of the city of Prague. On the other hand, we do have certain unused potential, especially in our research structures, university capacities. There are thousands of people who could be contributing to innovation in the boundaries of Prague, but we are seeing very little of that input of that human force to transform itself into real life tangible innovation that would then translate into economic power. This is why we, as the City Council, are encouraging events just like these, because as the technology is developing, we continuously or repeatedly have to make sure that experts across fields meet up and exchange knowledge on what is new and what are the new challenges, because at the borderlines of various fields there is the place where the leap-wise innovation and strategically important output really happens, rather than stepwise in the natural development within already commercial process. The X-ray imaging has been with people for decades, and so is computer-assisted tomography. I myself learned and used some of it some 20-25 years ago in my research career. Nonetheless, the advances of robotics and deep learning, which translates as AI in these days, open new fields, and we feel it because the city of Prague has thousands of kilometers of linear infrastructures. It has thousands of vehicles for various purposes, whether for taking care of the greenery, taking care of public transportation of all sorts. We are trying to see the opportunities for our own city and the companies we have founded to take care of the city in order to advance their processes, save labor, deliver a better service of the city to its citizens. So thank you very much for organizing this event. Thank you very much, all of you, for coming to this first one. I very much hope that you find it useful and that it will be the spark that will continue burning in the following years, and that we are going to see each other again and again. Enjoy the afternoon.
Thank you, Mr. Councilor, for your support and warming words. And now we can move to our next speech. It gives me a great pleasure to introduce Dr. Sascha Senck, Senior Researcher at the University of Applied Sciences, Upper Austria. Dr. Senck will present on non-destructive testing of electronic components using laminography and microcomputed tomography. Dr. Senck, you have the mic.
Thank you very much for the introduction. I will not talk so much about Robotic CT, but most of the, let's say, applications I show you can be easily transferred to Robotic CT too. What we like to do, or what we have to do at the University of Applied Science, we have a lot of industry customers and services, and we need to answer or solve their questions. And for those questions can be very specific one, and for this flexible kind of approach, for example using Robotic CT, but also standard CT, I give you some examples with a standard axial CT, but also with a special mode. It's called laminography mode, which is ideal for example, for scanning flat samples. And these flat samples could, for example, be a printed circuit board, which are used in electronics. We're having a research project we're working on together with TH Deggendorf, for example, what we saw already a talk today, which are, let's say, very difficult questions to answer. I will show you some batteries, and Josef already said everybody's scanning batteries, kind of easy. That's probably for some questions the case. What we always have to solve is a compromise between the size of an object and the resolution, scanning resolution we can achieve. So what you see here, for example, in the medical CT, form follows function, there's a human body, there's a gantry with an X-ray tube in here and a detector. What has to be minimized is the radiation dose. The harm from such a micro-CT or a CT scan cannot be greater than the benefit. And that's why there's rather low energies, but it's really fast. It can be seconds, but let's say close to a minute. What we do in industrial CT, there's no living being involved, so we can have longer scan times. We have a flexible setup. We can change, for example, the magnification, geometric magnification. So this is an industrial CT device with an X-ray tube, detector, and here's the object. We can move this one. We can use different detectors, for example, large 4K detectors, 2K detectors, single photon counting detectors, line detectors, and so on. And this is most of the time not an easy setup, let's say, because special questions have to be solved with a special setup. And in this case, we have high resolution for small samples, and the scanning time is rather large to have image quality, which is resolution, but also contrast and noise and so on, for industrial CT. This is the equipment we have, and we're the largest research group in Austria concerning micro-CT. I will show you at least three examples from samples of 3 of those systems. The left systems is for large parts, for high energy with 2 different tubes. But for lower resolution, but for large parts, for example, you saw a battery module, which consists of single batteries, dozens of them, and this one needs a high energy to be able to penetrate the object at all. And for the very high resolution and the special scanning mode, which can not, I will say not, but just hardly be solved using the 2 setups I just showed you with the medical CT or the industrial CT, is, for example, very flat samples. So they have an aspect ratio like a sheet of paper. It's very thin, but very broad. And there's a general, say, limitation. The larger the sample, the lower the resolution. And for our special case, I will show you, we are visualizing cracks. And cracks can be described as a 2-dimensional object, and this very fine structure. So this one is a difficult example. For, let's say, an easy example, what can be done easily? We have a micro-CT system, let's say with an X-ray source, with a detector, put the object, in this case a lithium-ion battery cell, into the CT, do, let's say, at least 1 scan, but 1 scan at the higher resolution is not enough. We need several scans, multi-axial scans, for example. So this scan here consists of at least 3 or 4 scans, and in the resolution we have to, let's say, adjust or reach for the questions at hand. This is scanning time of several hours, and several hours, we cannot do 100% scanning of each and every battery which is produced in the world. That's kind of obvious. So one thing is to make it faster, for example, using special reconstruction methods and scanning strategies. In this case, and this is the disadvantage what I want to show you, so advantages I will show you later, is that we cannot answer the actual question at hand here. Because from the producer of these batteries, or the user of these batteries, they didn't want to see the anode overhang or how well the cathode material is, but they wanted to do this separator. And the separator is a polymer foil, which is like 100 micrometer in thickness between very dense objects. And even though the contrast between high dense materials in this case, you see here also the steel parts with some cupping artifacts. The contrast is nice enough, but we cannot see the actual separator foil. Because if this separator foil is warped or ruptured, then this can lead to a thermal rundown. And if you have a 100,000 euro electric vehicle and has an accident, and you don't know if the battery is ruptured or not, you want to be sure. And this one definitely doesn't work for a whole car. Fraunhofer just brought out one, I guess, for a whole car with the Gentry style. This is not the resolution we are talking about. This is difficult. An advantage, nevertheless, is we can always use the 3D dimensional information. So we have, in this case, isotropic resolution of, let's say, 20 or 30 micrometer in X, Y, and Z. We can do the different slices. On the next page, there will be the top slices or the axial. This is just a video showing around. So if there would be a rupture, let's say here for the taps, for the current connectors, that will be kind of obvious. But still, this is done since years. This is kind of easy. What we want to see in general are features, internal features, and let's say anomalies, which doesn't look like it's supposed to look like, for example, for prototypes. And since micro-CT in general is not the cheapest metrology methods, let's say compared to, let's say, ultrasonic testing and so on, the benefits for the industry partners have to be fulfilled. And in this case, for example, we have here the delaminations, here's the tap, here's some delamination inside, and this is due to cycling. So the question was, can we see a difference with the new battery? Then we cycle it for 10,000 cycles with high voltages and so on, which is also a thermal regime, like in an EV, like in an electric vehicle. And how does it look afterwards? And can we still use it? How much is the capacity changed in between? So this is standard R&D questions for the companies we are working with. Usually we're looking at pores. I would say 50% of the analysis of the 3D data we are looking at is porosity. Because you have either porous materials, you want to have the 3D distribution, or like in carbon fiber reinforced polymer samples for aerospace, there are pores which are unwanted, or the laminations which are unwanted, and then this is scrap material. This can be done, like Josef said, directly at the airplane. If you have a mobile question, or mobile device, for us, we have to put the thing into our micro-CT. And our micro-CT can hold, like, say, 0.5 meter wide samples and 1.8 meter in height. And this is analysis we're doing just right now. And then afterwards comes the post-processing. For examples, I can quantify the anode overhang and so on. This is rather uninteresting for what we had in mind, because for the partners which we have, they are developing power electronics components, modules, for example, for DC-DC conversion, or for current conversion. For the loading, for example, very fast loading of electric vehicles. So everything here is connected to e-mobility. This is the CAD sample you see here, and this is the actual electrically loaded PCB, which we are taking a look at. So the edge length here is 8 centimeters. It's 8 centimeters in length and like 3 millimeters in height, and that is a very unfavorable object geometry for micro-CT, because you're restricted for the geometric magnification contrast. I will show that in a second what it is. So we have our sample. This is the 8 centimeter PCB. We get rid of the components here, so we can go quite near to the X-ray source. Then we maximize the FDD, the focus detector distance. And this one should be maximized to have this most phase contrast effects in our system. We have a rather low voltage applied. This is the maximum for the special filament in here, for the high resolution. And then we have approximately 5 micrometer. It's not exactly 5 micrometer. And also not in the depth. We only have this resolution, we will see that in a second, in 2 dimensions. And the 2 dimensions, if we have the analogy of this sheet of paper, is only an X and Y. I will lose information, most probably around this one. With the special reconstruction mode, it will get better. But that's ongoing research in any case. And then you don't have the rotating object here, but in this case, the source and the flat panel move in unison. So it's a translation in axial wise and not a rotational acquisition. So we have this limited angle artifacts and the loss of depth information and so on. That's quite clear. This is a disadvantage, but the major advantage, if we combine this one with this propagation-based phase contrast, is that we may be able to see the cracks inside a very thin layer of ceramics. This is the sample. I scanned 5 samples in total, have an overview scan. This one is not even at 30, but at 60 micrometer. I didn't put that one in the parameters. This one is at 30. And I can have a region of interest scan and take a look at the components from the electronics which I'm interested in. For example, here, we have the resistors, ceramic, metallic resistors, here's the MOSFET and so on. Yeah, this is, let's say, for an overview. This doesn't give me the information I want to have. I can take the 30 micrometer scan from the CT. This is 3-dimensional information, isometric voxel size of 30 micrometer, and I see also the parts. There's here in the resistors and in the MOSFETs here, especially in the solar, there's the pores. But that's not what I want to have. This one, more or less everybody can do in any case, because the pores in the solar, this is a common thing. 20 to 30 percentage of the surface, you can do that with radiography actually, is fine. And this is the actual board 2, so I will just take a look with you at 2 boards. This is here this overshoots effect for the high, in this case, voltage. And you see it in the photo, there's a black spot. And this is where the MOSFET, in this case, this fast switch for the DC-DC conversion failed. And then we take a look at the laminography. So this is now only the information about X and Y. And what you see, we have like a halo around the pores. And this halo, this white border here, this is phase contrast effects due to propagation, and that's why the FDD has to be so long, and interference pattern of the wavefront in the freeway. We have this edge enhancement, and this edge enhancement gives us these pores, but also those guys here, and this is not in the pores. I will show you soon in the video, because the solder is a soft material and the ceramic is a brittle material. The failure mode of a solder is not cracks in this case. It will rather, it will look differently. So this is an indication that we can see here the MOSFET, not itself, but the defects inside of the MOSFET due to these phase contrast effects, which have an edge enhancement involved. I will now play the videos, and I try to get to the pause button just by pausing this thing here. So this is the video, and now we see through the object, and here is the solder of the actual MOSFET. This one is the pores, and those guys here, this is the cracks in the MOSFET. I will just need 2 minutes, thank you. This is the cracks in the MOSFET. So what you clearly see, if you only have one focus plane for each of the slides, which is in focus, which is sharp, you can go through the single slides and see, in this case small, in the next case a bit higher, that the focal plane of the cracks is not the same focal plane like for the solars. And in this case, we don't see the MOSFET itself, but we have an indirect visualization of the cracks. These are the cracks here, and I took a look at 6 or 7 different objects in this case, and everything looks pretty much the same. So we see the pores, that's kind of boring, but we indirectly see the cracks due to the setup with this long acquisition time. And this one I already showed. Maybe for this it's not automatic, it doesn't matter so much. So for the rest of the 2 slides, I will give a bit of an outlook what we did in Austria, in this case concerning the robots. This is also, let's say, not the fancy use of robots, because in this case we have 2 robots which are loading and unloading at line a Zeiss, in this case, CT system, and they have several of hundreds of aluminum parts. And these parts, for example, for residues of the sand core, have to be scanned. And then the scan takes like 1 minute, and then they have the automatic defect detection in the background. But this is not robot CT in itself. Let's say it's a measurement for that one. We will use robot CT like what you showed shortly. And the second thing we are doing, we implemented a single photon counting detector into our RX solution system. We are working together with Advacam since the last years. We get really nice examples also for soft tissues, not exactly with the cadmium telluride example detector here, but with a silicon detector, but this now is ours. So we did a lot of experiments. Jonathan Klintz does the experiments here, and Sarah Heupel did the laminography scans. And this is an electronic part of a cut sample where there's also the solder joints and the pores in the solder here. This flies to space, so a high quality necessities here. They have to be analyzed, so it's worth doing it with micro-CT. And this is already one of the first micro-CT images we get of a high C material, the distribution of the lead and the solder and the pores and so on. And yeah, we're pretty happy about that already. This is it already. Please go to the homepage if you want to go to the ICT conference. This is some advertisements officially I do here. And thank you for your attention.
Thank you, Dr. Senck, for your very insightful presentation. And as usually, we have time for questions. So if anyone is interested in anything, please raise your hand and you will be given the microphone. Anyone? It was perfect presentation again. I really appreciate you use this sample. I didn't dream about it. So, it looks that everything is clear, so we can move to our next program. Thank you very much, Dr. Senck. The next presentation will be provided remotely from the New York State, and it is scheduled strictly to 14:30, and I'm not sure at the moment if we are already connected with Professor Wang. Not sure. So we can take 10-minute pause and then gather here again, and meanwhile we will establish the connection with Mr. Professor. Thank you very much. All right, ladies and gentlemen, welcome you back. Thank you for your patience. Professor Wang is connected remotely, and it's my privilege to introduce him to you. Professor at Rensselaer Polytechnic Institute and a leading authority in the field of tomographic imaging and artificial intelligence. Professor Wang is an esteemed expert in biological imaging and AI-driven imaging solutions, recognized globally for his pioneering work. His talk is titled AI-driven Robotics for Tomographic Imaging, and will focus on how machine learning and robotic systems are being combined to advance imaging, precision, and automation. Professor Wang, I hope we are connected properly, so we can please begin. Thank you very much.
Thank you very much for introduction. You hear me clearly, right? Okay, so I really appreciate this opportunity sharing our work with colleagues in Europe, and so I hope through this presentation and follow-up interaction we could develop some collaborative project. So my presentation, I hear echo a little bit, but anyway, so. And nowadays, embodied AI is a very hot topic. We talk about agentic AI and robotic imaging system and all other intelligent machines. So this is a very hot topic, and roughly speaking, we can consider so-called embodied AI or intelligent robot should have three kinds of functions, like sensing. You perceive the world, you collect the data, and in daily life we sense visible pictures. But in medical imaging domain and also industrial non-destructive evaluation, we talk about tomographic imaging, particularly X-ray imaging. So X-ray data serve as a very powerful tool, sensing the environment, also internal structure of samples or big structures. After images are collected, and we need to perform post-processing image analysis, that is so-called thinking process, reasoning process, or image analysis. And after that, we can take some action based on sense the data and the thinking results. So we take some action. The initial form will be modified scanning trajectory, so you can probe certain features or regions more purposely. And also, we could consider even advanced form of action, like robotic surgery and industrial environment. You can fix defect product. And in the nursing home, you can use robotic to give care. So a lot of exciting opportunities. So first, I talk about sensing part, particularly tomographic scan. And so this is the size of detector. In robotic imaging applications, this is a very common situation. So how do you extend the foundational tomographic model dealing with all these challenging cases? Metal artifacts reduction, important in medical imaging. And last year, we organized a AAPM CT metal artifacts reduction challenge. And the results is pretty interesting. Our major collaborator, General Electric, they developed a realistic CT simulator. You can generate CT metal artifacts in very realistic way. Then participants from international community develop many cutting-edge algorithms, and some of them give you very good metal artifacts reduction results. So shown here. So we briefly covered this sensing part. So so give you a sense of what's going on in this domain. Then the next part is so-called thinking and or image analysis. Once the CT images are collected, how do you segment relevant parts and extract diagnostic information? And also by name image analysis. And nowadays, as I already mentioned, foundation model is a very hot topic. We try to use an AI model that can take multimodal data, perform multiple tasks, not just a single task. Early days, we use AI model in a task-specific fashion. But now we think more generally, and how can we use one model to handle many problems. So this is a very brief timeline for AI foundation model development. And the recent achievement, very impressive. And initially, ChatGPT, and we use extensively, and it gave us a very, very powerful tool dealing with multiple tasks, like write a poem, like write a summary, and draft a letter, and so on. This is just amazing. And another recent achievement, as some of you know, the Chinese group developed this DeepSeek, and just similar performance, but the training and the inference time is orders of magnitude smaller than top-line model like ChatGPT. So this field is very hot. And along this direction, and we develop a medical multi-model, multitask foundation model for lung cancer screening. So this is a multi-institutional collaboration with MGH, Harvard Medical School, Wake Forest Medical School. So we have the code open, and you can test the code and the data set. The paper published in Nature Communications generated some news exposure, shown the video record here. And our foundation model dealing with big data, public big data, and also private data set from Harvard Medical School and Wake Forest University. The size of data set is about 300,000 cases. So the data set is very big, and the computing power needed is tremendous. So this is a brief summary of our computing resources. In our lab, and we have about this much computing power. And at RPI, supported by IBM, and we have 2,000 Tesla V100 accessible to academic groups. Our state initiated so-called Empire AI Alpha project, about 100 H100 available for us to train machine learning model. And our model, I just mentioned, got amazing performance, and compared to current state of the art. So our model, this blue bar, you see we got a significant performance gain. And given limited time, I cannot go into detail. Foundational model is very desirable for multiple purposes. And our model is specialty oriented for chest CT related tasks, and about 20 tasks. We get a very competitive performance with current state of the art. And the Holy Grail is a generalist medical AI model. And we believe this can be achieved through specialty-oriented models. After we have a good number of specialty-oriented foundation models, then we can do mixture of expert reaching this Holy Grail. and the model has scalability, and the larger model, the better metrics. And also we can generalize our model to other data set very well. So this is a very encouraging signal. There are multiple other benefits like explainability, and through heat map method, we see whenever model give you results, relevant features and the text will be highlighted in a meaningful way. So this is just a wonderful direction to pursue. So we have the foundation model for tomographic reconstruction and image analysis. And now we talk about a robotic imager. So we take some action. And we have been very interested in this direction decades ago. So this paper published in 2005, and we proposed a top-level design, so-called first clinical micro-CT scanner, focusing a small region of interest for inner-ear implantation. So at that time, this is our overall concept. We use a C-arm system to perform high-dose, high-resolution inner-ear imaging so that we can map cochlear implantation array clearly. And this is a rudimentary design. And recently, we upgraded the design. And as presented in this video, which received promotional prize by IEEE Access, so shown here. And we have Josef Uher here, organizer of this symposium, as our close collaborator. Also, my former PhD student, first author, my former student, Jim Bennett, also works in this domain. And I will show some of spin-off companies by my students, Mengzhou and James. So for this upgraded clinical micro-CT project, so we have this overall design. A conventional CT get an overall picture, but the resolution is not good enough. Then we use two robotic arms, get a good resolution, and improving current CT resolution 300 micron down to about 50 micron resolution. If you're interested, you can check our joint publication. So this is the robotic system from Joseph's lab, and some model animal scanning. And based on all these ideas and the results, we consider to upgrade our clinical micro-CT design using state-of-the-art hardware and software. So like X-ray tube, Sigrid is a company. They make most cutting-edge micro-focused X-ray tube, offering about 4 times greater X-ray flux at a microfocal spot. So this is the size. And also, Advanced and produces high-resolution photon counting detector. So we think this is best technology. And the robotic arms nowadays are quite mature. And algorithm-wise, my student developed a deep interior tomography algorithm. We only focus on a small region of interest. So truncated beam will introduce artifacts, and through deep learning, and we can recover the bias map. Then we recover the high resolution image. So this is the overall network structure. And when we talking about a very high spatial resolution, patient motion and mechanical instability is an issue. So to calibrate the imaging geometry, we need some innovation. So particularly, we propose to perform data-driven motion compensation geometric calibration. So So this works very, very well. You don't need to use a laser camera to measure source detector position. That's too hard. You just do scan roughly correct. Then we can extract accurate imaging geometric parameters using deep learning method. So this is the project we're talking about. The imaging company my student Mengzhou set up called Troy Imaging. So we're working along this direction. So this is Omni NDA and Jim Bennett set it up in Utah. So this is quite an interesting project. Let me see if I can play the video. Seems I couldn't play the video. But anyway, you will see the robotic arm drive source and the detector around this rocket payload firing cutout. You just scan line by line, get a very high resolution. Let me see. Oh, so you can take a look. Okay. So you don't need to use a very, very large detector plate. And with raster scanning, even smaller detector plate will do. So you can make a very flexible system, perform multi-resolution and various field of view. And this laminography approach is very powerful to reconstruct a plate-like sample, like this case. And you can do many other applications as well. So this whole data acquisition process takes about 2 hours, generating 100 GB data set. And in collaboration with box array, the Omni NDA and the box array reconstruct this motherboard with very high resolution. So this small region of interest, you zoom in a little bit, you see the imaging results is very impressive. So I imagine many other applications could be developed using robotic imaging. So from a foundational model point of view, so I feel this is very exciting. And the current foundation model, we know can translate a sequence of tokens, like a language, into another language, or just treat image as a sequence of patches. You can generate a sequence of descriptors of the image under consideration. And in the robotic imaging setting, we could just translate instruction into a sequence of steps. So how we move robotic arms according to task requirement. So this can be done by foundational model as well. So foundational model works as a brain of robotic system. And you get data, perform analysis. So there are a lot of interesting research directions to. Let me read the question. How do you integrate the data? Who is working on the actual problem? In our case, I just read the question. In our case, we collaborate with medical doctors. They collect the data, give us clinical problems, and interpret our results. We have over decades of collaboration. We work together very closely, very friendly, and clearly data is #1 important. And also we need domain expertise. And we as imaging engineer and scientist, and we can perform image reconstruction and can solve problems in collaboration with domain expert. Thank you.
Is there anyone else who wants to ask? All right. So thank you, dear professor. Thank you very much. We appreciate your lecture. You're connecting from the US in the morning, and hopefully see you again. Goodbye.
Thank you very much. And if any of you interested in exploration of interesting project, you can always send us emails. Okay, thank you very much.
Ladies and gentlemen, now it's time for our last coffee break, and it will be followed by a lecture by Dr. Jan Jakůbek from Advacam, and it will start at 15:20. I have just one notice. If you have your questionnaire, I forgot to tell you when and where you can return it. It can be returned at the reception at the entrance hall, registration hall downstairs. So please, if you have filled it in, don't hesitate to return it there. Thank you very much. Thank you for coming back. I hope you have had a pleasant and energizing break. We've even opened the windows to refresh you with fresh air. And now let's return to your seats and dive right back into today's program. We have more exciting talks ahead, exactly last two talks. And our next speaker is Dr. Jan Jakůbek, Chief Scientific Officer at Advacam. His talk is titled Imaging Modalities for Non-Destructive Testing Enabled by Photon Counting Detectors. Dr. Jakůbek is a physicist and imaging technology pioneer with hundreds of publication papers and a long history of innovation in X-ray detector design and applications. His contribution focuses to various applications of the photon counting technology in the field of X-ray, radiography, and especially for non-destructive testing. Dr. Jakůbek, the floor is yours.
Thank you for introduction. So that means that I am getting old, or what? So how to control this thing? Here. Okay, so I got inspired by Josef and I had to include also my old photo to my presentation. So in this case it is 1993 when I participated in some test beam in CERN, actually working with first like prototypes of those now called photon counting detectors. That time we didn't call them like that, we called them just pixel detectors. You see. Okay, and 32 years later, so we are here, and then this technology has evolved. That time I was working with Institute of Technical and Experimental Physics here in Prague under CTU. Then we established Advacam, and some like spin-off projects were created, and there is a group of companies which are using this technology, and many are collaborators and partners and customers. So we are pretty happy that it finally found some application field. This is not like just purely scientific thing. Okay, so I'm here speaking for Advacam. We are doing detectors, photon counting detectors. You have seen some results which were measured with those detectors already in the presentations of my colleagues. The number of applications is really broad, so of course radiography and different modalities in radiography, but also others. So we have our detectors in space, monitoring space radiation there. We are using them also for some medical treatment monitoring, like this one which is shown there for head cancer treatment. It is in Heidelberg, which is very nice. The basic principle of photon counting detectors is described here. I think that most of you know it. So actually we have always, if I would find the right button to point it, some sensor actually, which is basically semiconductor material. Ionization comes, the radiation comes, makes an ionization, which is then taken by electric field, directed to the pixels. And in the readout chip, so these are two chips. The first chip is sensor, the sensor chip is readout chip. We have a complete chain of electronics in processing the signal from each individual pixel for each individual event. So this is the big difference. Just to compare it with standard like analog detectors, which are very often called digital, but they are in principle analog, like CCDs, flat panels. In those, you would have, instead of all this chain of electronics, you would have just few transistors, like 3 or 5. Here in one pixel, we have 6,000 transistors, so it is pretty high integration. So if you imagine how many pixels we have, then it is more transistor than you would find in modern processors. And of course, then there is some chain of technological steps you have to do, starting from wafers, doing these interconnections, these bumps, integrating it with sensor. Now there is a sensor, and then you would have a functional unit. This is this, we call it assembly, sensor plus readout chip. And the biggest problem for a long time was the small size of the sensitive area of such device. And with the years, we developed the technology of tiling to place many of those units next to each other to cover larger and even larger areas to be well usable for radiographic applications. So main features for our technology is like a higher resolution of 55 microns per pixels, so these are square pixels. Since we have pretty complex electronics here, we don't only count how many photons came or how many particles came, but also we can measure their energy, so we can measure spectra per pixel, and we can measure also the time when the quantum of energy would come. I will later on show you some examples how to use it for radiography. And there are many other things. Since the information is present in digital form here, it is basically like a memory, then you have fast access to it, so you can read it quickly, you can have like continuous modes, you don't have to stop acquisition when you are reading out the previous frame, so just having here several registers, you would still continue counting while the other register would be read out, so there are many combinations of those things. I will not talk about these technical implementations, I will rather show some examples. We do some standard detectors, but here for this auditorium I'm showing some kind of exceptions. So we can do any like shapes, even some detectors with a hole in the middle. We did even some curved surfaces for some particular applications. We can do some multi-layer setups where the particles would go through all of them. We can make a long rows, thick sensors like those. So many different versions. Okay, but the main topic is X-ray radiography and modalities we can use with this technology. So the first big advantage of this photon counting principle is the dynamic range. So actually the information is present in digital form and we have a count number of photons. So there is nothing like 0.3 or 1.7. So there is either 0 or 1 or 2 and it can continue counting in fact forever. It is absolutely linear, so even after a long time, if there would be 1,000 photons, then half an hour nothing comes, and first next would come, you would have exactly 1,001. So actually, it continues linearity. And since actually the imaging noise, actually in such detectors, always Poisson distribution, which is square root of number of events counted, and then just counting more and counting more, we can make this noise smaller and smaller. So we can achieve very high dynamic range, which allows us, Josef already mentioned that, to see very tiny objects, in fact, on top of some thick structures. For example, this is the mouse body, you see bones, you see some soft tissue structures, and if you zoom in some region next to pelvis and backbone, here we saw such kind of like oriented structure, which is the hair fibers on the surface of the mouse. So you can see the one single hair fiber over the all thickness of the mouse. That's the first advantage, kind of like trivial. Next one, we can actually play with sensitivity to different energy bands. So we can set the thresholds, for the pulses we are analyzing in the pixels. That way we can sense the changes in the spectrum of X-rays when passing through some materials. And since this, let's say, the transmission spectrum depends very much on that material, that way we can distinguish different types of materials. So traditional X-ray imaging would give you just a grade of shades, while we can assign some colors to it, and we can clearly see the differences in composition. In some cases, you don't know whether some region is darker because it is just thicker, or it is darker because it is higher Z. We can see that. And as I said, this high dynamic range, it's really high, so it's signal-to-noise ratio can be in like orders of thousands. For example, this structure is carbon fiber reinforced plastics. One sheet of it, which is very often used as an input window for flat panel detectors. Maybe you saw it, this kind of dark surface, because it is considered to be transparent for X-rays, and it shouldn't actually cause any like change of contrast. And if we put it in front of our detector, we can nicely see all the like fibers and bubbles and different structures there. So it's like looking through like a dirty window and looking to the world outside. So here's just a few examples for this of these principles. This color imaging allows us to distinguish materials, as I said. Something very like common piece of PCB. If you do standard radiography, you can't see. This is some FPGA soldered using BGA technology, so there are some balls beneath, and you cannot see them actually looking, by eye. So you have to do radiography to check whether these balls are really there, whether they are present, and they are properly soldered. If you do standard radiography, you cannot distinguish actually these balls and the solder. And sometimes there are some capacitors, the blocking capacitors. If you do this spectral multi-channel imaging, here we used 3 channels. Then you can, I assigned virtual color yellow to solder, to tan basically. Then we can just check that if the point is actually shown in yellow, then the solder is present. And you can distinguish it from like tantalum capacitors there and other structures there in the PCB. Some other things, as I said, this detector is digital. That means it is fast, so one can do really thousands of frames per second. Here this video was taken at speed of 1000 frames per second because mouse heartbeat is pretty fast. So it's really like 11 hertz, so one could almost hear it. And using that high frame rate, we could nicely see different phases of the heartbeat, And you can see the change of the contrast, that the blood is pumped from this chamber to the lungs. So actually the contrast between lungs and this heart would reverse. And one can do this kind of like electrocardiogram, but this is not electro, but it is like radiocardiogram. To see like blood moves from atrium to chamber and from chamber to lungs and back. Next advantage, this is the same advantage just presented with different samples, the speed. So this is another application we were asked to do, to participate in a big project where the intention was to sort minerals according to content of certain specific ore types and to select actually pieces which would contain enough of this target material from pieces which are considered to be waste. Nowadays, everything goes to factory where it is grinded to powder, and then there is this flotation and chemical separation, basically producing this toxic waste plus this separated ore. If you would extract the clearly identified waste in advance, you would save energy, time, of course, amount of these toxic things produced. And on top of it, this waste material would be used for construction of roads or something, so it is not really turned into waste. So this thing, what you have seen, this scan is taken from continuous stream. It was 10 seconds, and during these 10 seconds we have seen 12 meters square scanned with a resolution of 55 microns. You see that the whole image is 500,000 pixels by 8,000 pixels roughly during these 10 seconds, but it runs continuously. And the speed of the belt is in this case 2 meters per second. So if I would come back to see it again, you see that basically the stones are just like jumping out of the belt, to this kind of tray, and there is a pneumatic set of pneumatic nozzles which would just plough or blow to certain selected pieces and blow it away to another tray. So that's how this sorting works. The same system can be operated in 2 energy bins. So we can have a colorless, we can separate some interesting regions, and based on amount of them we can say with certain probability how much of target material or target ore would be there. So that's the standard radiography, attenuation based. But there are also other modalities. I will show a few. One is X-ray imaging based on phase effects, which was already discussed or shown by Sascha Senck. I have different method of extraction of that signal, just to show you what is the principle of that thing. I have performed very scientific experiment on my terrace, actually, putting there is kind of glass vase or something with the water and some foam, on the surface, and there were a few droplets of water on the walls actually here. And if you put a projection plane behind, like a piece of paper, and you use sunlight, to make a radiography of that thing. So this is normal radiography we would see normally with X-rays. We start to see some things. First, actually, question I always ask my students is why we see it, because all the light which comes in comes out. So there is nothing opaque, everything is transparent. The bubbles are transparent, the glass is transparent, water is transparent. Because the light would change the direction of light. That's why we see it. So when we see different sections, so I have highlighted few. So behind of the foam, we see like darker region, which is dark field. So that means that the light was scattered out, so it doesn't continue straight. So it goes to all the directions. Close to like edges, we see this kind of enhancements because the light would be like directed to another place, and you would have more light coming here. So the light which would normally fall here, it comes here. So that's the phase contrast. And we have also such kind of like speckles. So if there are some droplets of water on the wall, they basically work as a lenses. So if you put your projection plane to right distance, you start to see these very nice, like always darker regions, and in the middle you would have very sharp and very bright spot. And all those methods can be used for imaging with X-rays as well. I will not speak long about that. And we all know that all these effects are also they depend on the wavelengths. So actually, if we would shoot to it with white light, we would see some rainbow, close to the edges. The same thing works with X-rays, just the angles are smaller. So you have to increase the distance to see that. So these are the principles. So light or X-rays, instead of continuing straight, it would be deflected or reflected. So there will be certain loss lines. So there will be some like darker, like line surrounding the edges in the image. And then next to it, there will be some like brighter region. And since it depends on wavelengths, on energy, and we can measure the energy, so we can perform two measurements. This image shows it. This is thin polyethylene strip, and you see this kind of enhancement of edges, dark and white. With one energy, this is shown in green here. The signal is bigger. With another energy, the signal is less, because the angle is different. But the attenuation is the same. So here it is recalculated to equivalent thickness to have it the same. So one can subtract these two images from each other, and you can get the signature of this phase contrast effects because the absorption is reduced. Okay, so that principle is used. For speckle patterns, we performed a nice experiment with mouse lungs. Because lungs, what it is, you have this alveolar structure inside, so it's like small bubbles, and they exactly can act as like lenses. So actually behind of this alveoli, in certain distance for certain energy, you would start to see this like bright spike in the middle. You have to always find the right distance and select the right energy, and then you see it. If you don't do that, then actually all the energies would overlap and you would not see anything. And the result is this, if you find the right place, you suppress completely the anatomy of the lungs, so you don't see these tracheas, you don't see the other tissues, you see only concentration of alveoli, everything else disappears, which is a nice thing, so you can really focus to certain shape of objects and localize it. This works also for porosity, by the way, for some plastic materials and such materials. The laminations, they were also discussed here. Exactly same principle I was showing for this edge enhancement can be used for that. We see laminations only when actually we can access the lamination in this tangential direction, So for flat samples it is difficult to do that. But luckily there are some structures which are like of this L shape. This is some thing from aerospace industry, and if you would vibrate with that here in this bended part, you start to have the laminated layers. So we perform the measurement, and really you see them nicely. So these are the laminated layers of laminate. Here the aspect ratio is very stretched in this direction. So this is 3 millimeters, while this is 30 millimeters. So it's just for display. So you start to see various features there. And there is some technique how to extract it using this approach that you have to take two images with two different thresholds, subtract them, and then you isolate the laminations. Everything else disappears. And of course, just by turning the object, you can make like 3D visualization of the shape of this laminated plane. So that's this modality based on change of direction of X-rays. I would like to spend also some time showing you another approach when we would look at individual hits. You know, here we still integrate the signal in the pixels with some conditions. We set the condition that we would like to see only selected range of wavelengths or energies, but we can look at each of them individually and collect a list of all the events detected, all the photons detected, and then analyze them from such a long database. There is a certain family of chips called Tampixes, Tampix 3, Tampix 4, for example, and in every pixel we have ADC basically integrated. So every pixel can measure an energy spectrum. Just as an example, I show here European 152 with many peaks. So we really measure the spectrum of this incoming radiation. There are some like bonuses. Sometimes of radiation they are seen differently than just like being like single pixel hit only. So we can see tracks of muons as Uwe said, or we can see this kind of like snowflakes, which are alpha particles from the radiant decay in the air. But this is very rare, you know. And you can select or separate them or identify them and suppress them. If you are interested only in X-rays, you would use just these dots there. And if you can do that, then you can use this detector very nicely, for example, for XRF imaging. So you take, again, a piece of PCB in this case, shoot through it with X-rays. X-rays would excite these materials, and they would start to emit characteristic fluorescences. And then you perform exactly this type of measurements. That every pixel records the spectrum, and then you can go through different channels of that spectrum, showing content of different materials according to their characteristic X-rays. So this is a PCB, this is painting, so there are some pigments, there is the XRF image of the same thing here, and I will show you also some applications for X-ray diffraction measurements. So I will maybe skip this slide. It's kind of like overview of everything, but not saying much. I will jump directly to this XRD stuff because this is connected very much with material structure analysis. And we are talking here about defectoscopy mostly, and material structure is a very important part of it. You know well that actually if you would have a Japanese sword, then it would probably be made differently than some piece of whatever metal like can, you know, so it has to have different crystalline structure. So to check it, people use this XRD setup, shooting to the sample with a collimated XRD beam. At certain angle, you would start to have this reflection, typical for specific crystalline lattice. And you perform a scan, changing this angle, and in the same time you would change the angle of the detector, and you record basically such a spectrum where here you have an angle, and here you have intensity of reflected beam. And you are looking for peaks here. You are trying to localize the specific angles where you see the reflections, which are typical for crystalline structures. But unfortunately, very often, you don't have only the XRD reflected beam, but you have also some scattered radiation coming out of the surface. There could be also fluorescence coming from the sample. That's pretty often. And this background actually, you know, unfortunately carries also some noise. So your peaks are, of course, seen on top of this noise. And to be able to separate them, you need to have high statistics. These our detectors, they have nice feature because they are spectral, so we can select certain energy band. And since we know that this X-ray tube, this is very often X-ray tube with copper target, and people are detecting fluorescence of copper, which is 8 electron volts. So we would like to select only 8 electron volts, which is this red peak here, and okay, alpha of copper. So if we do such a thing, then the background in this measurement drops here, in fact, by a factor of 30. Then the SNR is improved by a factor of 9, and you start to see even peaks which are very difficult to be seen in the original measurement. So either you would have much higher sensitivity, or you can make much faster scan, so increase the speed of scan by a factor of 10, in fact, which is, you know, reducing it from like half an hour to 3 minutes, which is pretty big. What I will show you on top of it is something which was difficult to do before, because this previous method used energy of 80 kiloelectron volts for measurements. So that means that you could analyze only the surfaces of the samples. You couldn't go to the volume. In some cases, if you are welding something, the volume is important, of course, much more than the surface. So to be able to do such a thing, you have to let the beam to go through volume of the sample, but it has to be energetic enough to penetrate it. Then actually it would be, of course, reflected from some grains, some crystals, and it would create this kind of images we have seen before. But normal detectors, which would not have this capability of spectral measurement per pixel, would see such a kind of like fog. They would not see any like rings, nothing where you can calculate the angles, and based on the angles, you would be able to judge what is the sample. Our detector can see that, so it can measure these energies. So for each energy channel, you would have specific image like this. Sum of all those gives you this kind of fog. And then actually you can recalculate all those measured diffractograms to like one common energy and sum them up and reconstruct back like full diffractogram of this sample. The beauty of that thing is that you can use polychromatic beam from X-ray tube. You don't have to go to synchrotron. Normally people would do it with synchrotrons, going up to like 100 kiloelectron volts energy. So you don't have to do that. And on top of it, since you use full spectrum which goes through, all these channels are used. You greatly enhance sensitivity and speed of that measurement. So Josef already shown this image where you have two pieces of stainless steel welded, and since actually both these pieces, there were, I think, the thickness is 2 millimeters in total, 1 millimeter each, and they were made by rolling. And if you do rolling, you would orient the grains inside of the sample, and then actually you would not get circle, because not all the angles would be happening with the same probability, but you would always get this kind of like maxima here. So one sheet was rolled in this direction and another one in this direction. So having them both welded like this, you have this kind of 4 peaks here. But if you go closer to the weld, where the area was heated up, and then it recrystallized again, but it recrystallized homogeneously. So this orientation, this texture disappeared completely, and we see that it is isotropically distributed again. So you basically lose certain material properties because of the welding. So that's something you can do and going across of the full thickness of the sample. There are many other examples. I will show just a very last one which we processed just recently. We said, okay, since it is very fast, we can do these measurements in really milliseconds. So because we use all the spectrum, so the duration of the measurements can be like a fraction of a second. So we can watch also some dynamic processes. We took this plate of steel, we put it to some setup, we heated it up to 750 degrees C, and we wanted to see recrystallization of this steel from martensite to austenite and back during the cooling. So here you see the sample. Here there is the setup. Sample is hidden inside. It was pretty complicated thing. There is X-ray tube with collimators. The detector is here behind. And during the heating, actually, at the beginning we saw such a pattern behind. Then actually the pattern have changed. If you will be careful enough, you will see that this kind of like secondary rings are not there. They are kind of blurred. And then if you cool it back, then it appears again. One can prepare very solid model for it, and here I am showing actually what happens. This spectrum here, these are angles here and intensity. These are peaks, typical for martensite structure. Martensite is this one for low temperature, and there is always like blue line and red line. Actually, red line is the model, blue line is the reality, the measured reality. It fits perfectly. And actually, as you are heating it up, you start to see a big change. So now it dramatically have changed. So now actually, like 95% of that already recrystallized to austenite. But we unfortunately switched off the heating too early, so it was still actually continuing this recrystallization. Then we switched that off, and it started to decay back to martensite. and we ended up with martensite again. And analyzing this data, so what you have seen, this is reality, we could really find the content of martensite and austenite with precision better than 1% across of the full thickness of the sample. So that was amazing for us to see that it was such precise, the measurement. So we are already pushing to stop. Okay, let me just show maybe last slide. I will skip everything. This principle, actually, I have described that we are measuring the signal in each individual pixel allows us to do some improvements of quality. Very often it happens that our photon would hit kind of like point in the pixel which is close to the border of the pixel, and then part of the signal would be detected by neighbors. So instead of having like one pixel responding, we would have several. So we would have cluster. And such a cluster, each pixel in this cluster would give us amount, how much charge, how much signal for that one event is seen. That means that for that single event, we have 4 numbers measured, and it allows us to calculate 4 another things. So for example, we can calculate precise hit position in X and Y with better precision than one pixel. So this would give us 2 numbers. And then we can calculate depth of interaction, and we can calculate the energy which was lost. Because actually, if we have a detector like this one, which is of certain thickness, if the detection occurs close to the surface, then the charge has to be transported down. You can have some charge losses during the transport. For cadmium chloride, it happens. With silicon, we don't see that. So actually, we can improve all those parameters we normally have. So position would be improved, depth would be determined, and energy would be improved. And just to show you the result, so this is the result. This is this IQI measure or standard, which was described by Uher here. This is the first generation of the standard, which went down to 50 microns, and we distinguished those wires perfectly. And the second generation, it goes down to 20 microns. This is this pair of fibers, 17D17, and even those are recognized well. So actually, we still distinguish it. So that means that we cannot measure resolution of our detector with this standard. So the standard should be updated. So, and the effect is that, for example, these chips, it was shown here by Sascha, this tomography of integrated circuit or PCB. This is the same situation. There is also chip wire bonded, and if you don't have this feature, you see here it's just a cloud, but here you see distinctive bonding pads actually in the detector. There are many other things I don't have time to talk about, like gamma camera, improvements of spectra, backscattering I wanted to touch, but maybe I'm pushed already to stop. So maybe I will just show this slide. Beauty of backscattering is that actually even very small signal gives us already information. If we are doing standard radiography, we are basically measuring a loss of intensity. So we have to first know what is the intensity, we put there a sample, and we see that there is a difference. To see, you are basically subtracting these 2 big numbers with certain noises, and the noise accumulates. Here, if you are shooting to some object, actually, you shoot with this like beam, and you look what scatters back. If nothing scatters, that means that there is no material. If you have just one photon scattered, that means that there is a material. So there is such a simple measurement. So this is kind of thermal insulation for some concrete structure. So it is pretty known scenario. And of course, people are interested whether this hydro insulation in between is still really there. So we wanted to see this like polyethylene foil, like 200 microns thick. And you cannot access it actually from other side. You don't want to remove all those panels. You don't want to damage it. So you do this measurement, and you see the foil here inside, and you even see some kind of gap behind if there is. And if you would look carefully, you see that actually in this image there was some muon which came during the measurement time. So actually all those points there are like single photons only. But already this thing is enough to see the structure. So we don't need to have many photons. We need just few. And then you have already a usable signal. Many other things, corrosion and that thing, such things. That's it.
Thank you very much, Dr. Jakůbek, for your insightful talk, and sorry for pressing you by standing here. Now we have still a few minutes for a discussion. So if there are any questions, we are ready. Yes.
So the detectors we have tested, you mentioned that are quite small. What is the perspective? How large can you do the detectors? And what substitution of classical DDAs do you have as a competition?
The largest we have done was this detector. We always name it according to like number of tiles. The largest was 10 by 10. That means like 15 by 15 centimeters. There was a picture somewhere in the beginning of the presentation. And but with the time we realized that many people would optimize, let's say, the price and performance that way that they would prefer something asymmetric. Instead of having a square projection plane, they would rather have like a stripe, which can be then used for scanning. And the other case which I wanted to show was this thing, because here the conveyor belt was 40 centimeters in width. So this detector was 40 centimeters long, actually. Yeah? And here we don't have to have a really, large area in the other dimension, because everything moves through the sensitive area. So actually the length matters. So it was, the detector here actually was this 7,680 pixels by 256. You see no problems, actually. You don't see them. No. Actually, the truth is that actually the edge pixels are twice as large. So normal pixels within the matrix would be 55 microns, and pixels along of the edge are 110 microns in size.
Thank you very much. I see another question.
Coming to think of it, wouldn't it make sense to double the counter depth of the periphery pixels then?
For what?
To double the counter depth of the periphery pixels.
Yeah, but you know, the advantage is that there is a speed. You know, so actually you can read out the data very quickly and then sum them up in the computer memory. So you don't lose anything. You know, it's different from analog devices where you always have to perform ADC conversion. Then save it in the computer, and then you perform an additional one. And the additional one can have different linearity, different offset, and this is problematic. Here it is not, so we just continue counting in the computer.
Okay, so on the transmission application you showed us, so each of the round images, the round signal, is according to each element, or what?
What do you mean?
The transmission XRD.
Transmission XRD. Ah, yeah, transmission XRD. Okay, this stopped to work. What? What should I do? It doesn't do anything. Okay. Yeah, I was pretty quick there right now. So these were these speckles. The laminations, these things. So how it works actually, it was shown actually here.
Yeah, this one.
So you see there's like a grain, which are like monocrystals. Yeah, and each of them has certain random orientation, or people would like to believe that it is random. Sometimes it is not random. So if actually this orientation of the crystalline planes would obey this Bragg law, so the angle of incidence of this incoming beam would be equal, or would satisfy this condition actually, then we would get constructive interference, and then actually would have very high intensity seen for that particular wavelength. Other wavelengths would not do anything. There would not be interference. So, and since you have all the wavelengths present, then also other crystals which would not have right angle would fulfill this condition for different wavelengths. So all of them would cast some reflection to some direction, but for different wavelengths. So for us it is very advantageous that we have polychromatic beam, because then some wavelengths would satisfy the condition for each crystal. So that's how it works. And since the angle is given, but only like angle of deflection or reflection, then actually it can occur to all the, in 3D for all the other angles. So it would typically draw kind of circle if the grain would be very fine and isotropically oriented.
And the source is
X-ray tube with polymeter.
It's a normal X-ray tube.
For example, for this martensite austenite transition, the collimator was 1/2 by 1/2 millimeter, pretty thick. It was nothing like special.
Yeah. Okay, thank you.
Thank you very much. I think we have time for last 2 questions.
Yeah, very interesting talk. Thank you. So I noticed that you use different power sources sometimes. And do each of these techniques, are they optimized for a particular source power, or does it?
Yes. Unfortunately, yes. This is like, let's say, bottleneck of this method, because this ADC actually in the pixel works only if the number of counts is low. So actually, one of these detectors we normally use, this Timepic3, can give you up to like 40 million counts per chip. But in the chip, we have 65,000 of pixels. That means that every pixel can have up to 100 counts per second, which is not enough for normal radiography. Luckily, there is a new chip which is 32 times faster, so then it will be like 3,200. For nanofocus sources, it will be fine because they are of low intensity. For radiographic sources, for NDT, it is far from actually the intensity people would use. So still there is a long journey to make them faster. Yeah. So that's the bottleneck, that we cannot be very fast. That's why actually we use these detectors for these applications where the intensity is low, like backscattering, XRD, XRF, or attenuation if it is measured with isotopes, for example. If you have isotope, then it is not that powerful as X-ray tube, and you would benefit of spectroscopy because you can separate only a certain peak and you can suppress Compton or reconstruct it even. So these are the advantages of these detectors with the ADC. But counting would work normally. And all these detectors, they have always both modes. So if there is this ADC, then there is also mode which supports just counting.
Okay, thank you.
Thank you, and I saw another one.
In the phase contrast images, do you have used your spectral fencing? Because you always need some coherence, energy coherence.
Spatial coherence is necessary here, So we have to have a really microfocus or nanofocus source here. So spatial coherence is enough to see
But the energy coherence?
Actually, if you energy cuts are okay, So you see it even without any. Actually, like Sascha was showing, So there was no actually particular energy selection, for that. He was using like propagation-based separation of these phase effects. Or here I used like energy differences that actually each energy would deflect differently, because it creates this like rainbow thing. So, but you don't need any special.
If everybody is satisfied, we can move on next talk, and thank you, Dr. Jakůbek, for your inspiring talk. The very last one presentation is ahead of us. The talk is called From Van Gogh to Raphael, Robotic CT in Art History. This talk was supposed to be presented by co-founder of the Inside Art company, Jiří Lauterkranc. Unfortunately, he is not able to be here due to his illness. So for this reason, this presentation will be presented by our esteemed Josef Uher, who is also co-founder of the company. Josef, it's yours.
Okay, thank you. Long time no see. Okay, so I already mentioned that all these technologies have a variety of applications, Jan said as well.
And one of them is inspection of art. Dr. Kotterli was talking about it as well from the forensic perspective. Jiří, if he was here, he would be speaking about use for restoration and conservation of art. Unfortunately, I really don't know much about it, so I will again look at it from the perspective of the technology, which hopefully will be also interesting for you. Anyway, for the art inspection, we are using exactly the same machines that we are using for aircrafts and cars and whatever we are scanning. Only for purpose of art inspection, we call it a little bit differently. We call it R2. It's a little bit joke. But detectors, X-ray sources, all is the same, including actually the reconstruction software. So everything that I will be showing for art here applies also for any kinds of applications as well. So yeah, we are still talking about transmission X-ray imaging. Again, no need to dive into any details. But if we use the X-ray imaging for art, then we can see the hidden layers, of material underneath. So if we have example of painting here, then if we take X-ray image, you can see that actually the original painting was something totally different. We also heard from Dr. Kotterli that this is a strong indication if the painting is or is not false, fake. However, sometimes it happens that painters were actually reusing canvases, and if art restorer or conservator is working on the painting, they need to know the structure of the painting, and they need to understand how the painting was created in order to do the correct treatment of the painting. So very often X-rays are very useful, but at the same time not sufficient, because we see the structures, but we don't really see many differences between these pigments. And that's a common limitation of standard X-ray imaging that you can have, and Jan also mentioned it on one of his slides, that you can have materials which are of completely different composition, but depending on combination of thickness and density, you can have the same X-ray signal behind them, and that is somehow limiting the detectability of materials in structures, especially paintings, because paintings are a collection of all kinds of minerals and pigments that these artists are using. So X-rays are giving us nice structure, same as a black and white picture. We know it from old times when we had pictures which were only black and white. So in this case, if you look on this location, the gray value is the same, so we can nicely see the structure, but we cannot really say, are these two pieces of glass different? If we have color X-ray image as a color image, color photo, we can nicely recognize it from each other. That's quite simple. So the question is if it works for X-rays, and obviously you already know very well that it does. We have our photon counting detectors, so we can do it. It is also a method which is commonly used on synchrotrons, which are able to select a given wavelength, so they can tune the accelerator for a given wavelength. And you can take an image below and above, so-called K-edge, which are characteristic features in properties of elements. And you can take two images and you can subtract them and you can get a map of the given element. So that's a very common technique, works very nicely, but you have to have synchrotron, you have to have big accelerator. So this is also the reason why this technique is not that commonly used, because you have to arrange the access to the accelerator and so on. But with our detectors, we can actually do it not on the source side, we can do it on the detector side. We can measure the wavelengths on the detector side, and we can generate a color image where the colors are associated with differences in these materials. So in this case, we are not yet saying which color is which element. We are just saying, look, here are differences. And that turns out to be very much sufficient for many situations, especially in art inspection. So if we go back to this painting, so that's the black and white, as you saw before, and this is the color image where the colors, pseudo-colors, are associated to the differences in materials. If you look more in detail, black and white image, and then color image. Now, this is quite important, because if you look on the black and white image and you would like to do subsequent data analysis or analysis using some other methods, electron microscopy, for example. So at that point, the art historians, art restorers have to take samples. It's not non-destructive at that point. They have to take a sample out of it. But should they do it here or here or here or here? Hard to say. But if we see the differences in materials, it's obvious that samples should be taken in this location, this location, this location, this location. Yeah? So it really gives very important information to have a comprehensive information about the painting, or let's say take samples that give the comprehensive information. So if you look some more examples, so this is a painting, we scanned it, and we also did that with different imaging devices. So not only that we have these colors, but you can see the differences in image quality. So imaging plates, so sort of reusable films, that's here, flat panel is here, and our scanner is here. So you can clearly see that, for example, the contrast, the contrast in combination with the resolution is much better compared to the standard technologies. Plus we have the pseudo colors, so we can recognize these materials. This is the same, but more in detail. So imaging plate, quite good resolution, but noisy. Flat panel, less noisy, but not at very high resolution. And our photon counting detector and the robotic scanner. And colors, of course. And here comes some examples of a variety of scans that we did. Since we have the system portable, the mode of operation always was that we packed the machine and we drove somewhere. So in this case, we loaded the system into my little Škoda Octavia, and we drove to Denmark and spent 1 week measuring there in the National Gallery. So here is one example of the painting. So in this case, what you see on the surface, we did see in X-rays and then colors. So this one wasn't terribly exciting. Here is another example of the scan we did there. And this is more interesting because you can see that there is somebody was overpainted. So then, in this case, this is then work of art historians to decide if this is okay or if it means that there is something wrong with the painting. Yet more example as it looks on the surface and how it looks underneath. Totally different. Actually, again, I'm not expert on art history, but it's quite funny to hear people who are, and they, for example, explain me that many of these paintings were the approach in the past wasn't so like today, that we would like to conserve it and we would like to keep it forever. Back, hundreds of years ago, if they didn't like the painting anymore, they just repainted it with something else which they thought is better, and they didn't care too much. Anyway, so this is one of our favorite paintings because it has a nice story behind it. This was confiscated to Sicily mafia, and gentlemen from Monaco bought it relatively cheaply. And of course, because it has a signature Vincent van Gogh, he was wondering if it's really expensive painting or not. And first war, and it is Serbian soldier. And on top of that, when we scanned the whole thing, we discovered that there is a still life in the corner. So Jiří agreed with the owner that he will sort of bring the painting to the original state, so making the civilian back into a soldier, and also uncover the still life in the corner. And so this is the result. Why anybody overpainted this? Nobody knows. This is still a mystery. But yeah, you can see the difference. Now, you have seen this slide already. So I said that this painting was original Raphael's painting. It also has a long history. I don't want to speak about that, but it was quite complicated at some moments in time. but again, Jirka was restoring this painting, so this is really, there are only few people in the world who had a chance to do restoration of this kind of painting, so he's really top league at the moment. And again, he requested to do an X-ray scan, which meant to pack again our system again into my little Škoda and drive to Switzerland and do the measurement in a bank there. So we put up all the system and we did the scanning. So you can see the painting as it looks, and here is the X-ray image, standard one. And then we did it, of course, in spectral mode, and here are the individual pigments that we identified here. So this is kind of the inputs that go into generating the color image. And just to prove you that we are not really inventing something here and it's real, there was done also XRF mapping. So spectrum of XRF photons was measured here, and you can see clearly the difference here. So there are peaks that are belonging to copper and lead, and here is only the lead. Yeah. So indeed, the colors that we are showing are corresponding to differences in elemental composition. And again, in the standard X-ray image, you cannot really say, if there are any differences. And here are some pictures from the measurement. So there were some questions about radiation protection. So in this case, it was relatively straightforward because it's a bank, it's a vault, so there was plenty of space and we could be far away from it, and there were concrete walls and steel walls, and there was no problem whatsoever. Another thing that we had to do, because it was already too high, so we had to kind of swap the orientation of the source and detector sort of midway during the scanning. Obviously, this is faster video just to show the concept. And you can see they do this kind of wiggle just to avoid cables to be rolled on the robot, but they come back and continue the scanning. And some overview. So you can see it here, so concrete wall, some steel wall here, and then we were sitting, the measurement took place here, and we had our, let's say, station a few meters away from that, and it was perfectly fine. Of course, art pieces are not always 2D. Most of the pieces are 3D, so that's what we do as well. So here is example of a scan of a sculpture. This is a measurement we did here in Prague together with National Gallery, and we are measuring a full CT of a sculpture there. And this is the result, pretty much standard CT. And here are some more examples of scans we did. Some of them are quite scary. Actually, I have to say some of these paintings are really ugly. I don't know why people are buying it, but anyway, I'm a physicist, so I don't understand it. Yeah, some sculpture from Asia. Again, Mr. Kotily was mentioning that these kind of tree rings that we see in the X-ray image could be used for dating. So there are databases of tree rings from different areas, because the width of the tree ring is telling something about the weather condition in given years, and then you have those sequence of weather conditions throughout years. So if you look on that sequence, you can very precisely estimate what is the age of the wood used in the structure. So that's quite common technique, but you need to have some sort of way how to see these tree rings, and very often that's done destructively. So they drill through just to take a sample, but of course computed tomography is much better. You don't need to destroy it. And here is another example, Wang statue. And violins. We scanned also 2D image, and we also looked on some tomosynthesis here. The contrast was quite wide in this case. So there are all kinds of, let's say, objects that we scanned over time, and we are still doing this as a service. Well, now and then customers are coming and we are doing measurements for them, scanning mostly paintings, I have to say. Yeah, so that's just a summary and conclusion. But basically, from my perspective as a physicist, art pieces, airplanes, or any other industrial structures are more or less the same. It's the same physics behind it, you know. So thank you very much for your attention.
Thank you very much, Joseph. Are there any questions? Yes, we have one.
Nice job, Josef. So you had all those elements, and you had all the different colors that you. Are those actually defined by the spectral response of the element?
Yes. Yes.
Okay. So
yes.
you have the ability to truly identify the actual elements built into the paintings. Or is there what are the limitations there?
Yeah. Let me get there. So.
Thank you. We are on time. Great. Ladies and gentlemen, this concludes the official part of the first RoboCT user forum. You are now warmly invited to stay with us for the evening networking party, which will continue until 22. Here, all the halls and rooms of the residence are available for you, so you can use. Of course, there will be dinner. Of course, there are the B2B meeting rooms and so on. You can use it all. Sorry?